You're moving at 670 million miles per hour right now. As you sit there reading this, your body is hurtling through space at a speed so incomprehensible that if you could somehow feel it, the acceleration would tear you apart instantly, and you have no idea where you're going. This is not a metaphor, it is a measured fact. Your planet is orbiting the Sun at 67,000 miles per hour. Your Sun is screaming around the centre of the Milky Way at 490,000 miles per hour. And the Milky Way itself, along with every galaxy in your cosmic neighbourhood, is being dragged towards something we cannot see, at speeds that make every other motion look like standing still. 670 million miles per hour. All of it, all of us, moving together toward a destination we did not choose and cannot escape. For most of human history, we believed the universe was still, fixed, eternal, a painted backdrop against which Earth alone moved. Then Edwin Hubble pointed a telescope into the dark and discovered that everything, everywhere, is flying apart. The universe is not static, it is expanding, accelerating, and the force driving that acceleration is something we have named but do not understand. Dark energy, an invisible pressure that makes up more than 2/3 of reality and is pulling the cosmos toward an ending we are only beginning to predict. But before the end, there is the journey, and the journey is stranger than anyone expected. Hidden behind a veil of galactic dust, there is a gravitational monster called the Great Attractor, pulling 100,000 galaxies into its grip. Andromeda is racing toward us at 250,000 miles per hour, and somewhere far beyond what we can see, the universe itself may be headed toward a fate more unsettling than darkness. This is that story. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. From stellar motions to ancient radiation, we will follow the evidence that transformed the sky into a living archive. Then we will confront the forces that shape tomorrow, and the possibilities waiting beyond the horizon of present human knowledge. You are moving right now, not in the way you think, not because you shifted in your chair or glanced at your phone or took a breath. You're moving through space at a speed so absurd that if you could somehow step outside your own reference frame for just a moment and watch yourself go by, you would not believe it. Right now, as you sit there, you're travelling at roughly 670 million miles per hour through the universe. Not around something, not towards something you can see, just moving, carried along by forces and structures so vast that human language has trouble even naming them properly. And the strangest part is that you have been doing this your entire life without feeling a thing. That number, 670 million miles per hour, is not a metaphor. It is not an exaggeration for effect. It is the sum of all the different layers of motion you are participating in at this exact moment, stacked on top of each other like a nested set of conveyor belts, each one moving faster than the last, each one carrying you further into a destination that nobody on Earth can clearly define. We know we are going somewhere. We can measure the speed, we can map the direction. But the endpoint, the reason, the thing pulling us forward, remains one of the most profound mysteries in all of cosmology. Most people, if they think about cosmic motion at all, picture the Earth spinning on its axis. That is motion, sure. The surface at the equator is moving at about 1,000 miles per hour, which sounds fast until you remember that the atmosphere is moving with you, and the ground beneath your feet is moving with you, and your body has never known anything else. You do not feel it because there is no difference between you and the thing carrying you. You're not moving through the air. You're moving with it. The whole system is in sync. Then there is the orbit around the Sun. The Earth is not sitting still in space. It is flying around our star at roughly 67,000 miles per hour, tracing a near-perfect ellipse that takes 1 year to complete. 67,000 miles per hour is fast enough to circle the equator in about 22 minutes. If you could somehow stand still in space and watch the Earth go by, it would scream past you faster than any bullet, faster than any jet, faster than most things humans have ever built, and yet you feel none of it. You wake up, drink coffee, go about your day, and the entire time you're hurtling through the void at a speed that would rip apart anything not held together by gravity and inertia. That is just the beginning. The Sun is not sitting still either. Our star, along with every planet, asteroid and comet bound to it, is orbiting the centre of the Milky Way galaxy at roughly 490,000 miles per hour. The Sun is located about 26,000 light-years from the galactic core, out in a spiral arm called the Orion Spur. It takes roughly 230 million years to complete one full orbit around the centre. The last time our solar system was in this exact position in the galaxy, dinosaurs had not yet appeared on Earth. The next time we come back around, if humanity still exists, we will be so different that calling us human might not even make sense anymore. 490,000 miles per hour. Think about that. You're moving nearly 500,000 miles per hour just because the Sun is falling around the supermassive black hole at the heart of the Milky Way. And you cannot feel that either. There is no wind, there is no vibration. The stars in the night sky stay exactly where they have always been, at least on human timescales, because they are all moving together in the same immense rotation. You're inside the ride. You cannot see it from the outside, but it does not stop there. The Milky Way itself is not stationary. Galaxies do not sit in place like stones on a table. They move, they fall toward each other. They collide, merge, rip each other apart, and reform over billions of years. Our galaxy is currently falling toward the Andromeda Galaxy at about 70 miles per second, roughly 250,000 miles per hour. In about 4 billion years, the two galaxies will collide, not like cars crashing, more like two clouds of stars passing through each other, their gravitational fields tangling, their shapes warping, until eventually they settle into a single larger galaxy that astronomers have already nicknamed Milkomeda. By the time that happens, the Sun will be nearing the end of its life, and Earth, if it still exists, will be a burned cinder orbiting a dying star. But the motion, the fall toward Andromeda, is happening right now. It has been happening for billions of years. It will continue happening whether we are here to see it or not. And that is still not the final layer. The Milky Way and Andromeda are both part of a small cluster of galaxies called the Local Group, and the Local Group itself is moving. Not randomly, not in some chaotic tumble through empty space. It is being pulled. Something out there, something massive, is exerting a gravitational tug on our entire galactic neighbourhood, and we are responding the way everything with mass responds to gravity. We are falling toward it. When you add up all these motions, Earth spinning, Earth orbiting the Sun orbiting the galactic centre, the Milky Way falling toward Andromeda, the Local Group being pulled toward some unseen gravitational anchor in deep space, you get a number that does not fit comfortably in the human brain. 670 million miles per hour. That is the speed at which you, personally, are travelling through the universe relative to the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang. The cosmic microwave background is as close to a universal reference frame as we have. It is the remnant heat of the moment the universe became transparent to light, roughly 380,000 years after the Big Bang. It fills all of space, and it is almost perfectly uniform in every direction. Almost. There is a tiny asymmetry in its temperature, a slight difference between one side of the sky and the other, and that asymmetry tells us we are moving. Fast. For most of human history, none of this was even imaginable. The Earth was the centre of everything. The stars were fixed lights on a celestial sphere that rotated around us. The Sun, the Moon, the planets, all of them existed to serve the story we told ourselves about being the point around which the universe turned. That model was not stupid. It was based on what people could see. If you stand outside and watch the sky, it really does look like everything is revolving around you. The Sun rises in the east, arcs overhead, sets in the west. The stars wheel across the night in perfect circles. There is no sensation of motion underfoot. The ground feels solid, stable, unmoving. Why would anyone think otherwise? It took centuries of careful observation and a willingness to admit that human intuition might be wrong to overturn that picture. Copernicus proposed in the 1500s that the Earth was not the centre, that it orbited the Sun along with the other planets. That idea was not popular. It contradicted scripture. It contradicted common sense. It made humans feel small. Galileo, a few decades later, pointed a telescope at the sky and found evidence that Copernicus was right. He saw moons orbiting Jupiter, proving that not everything in the heavens circled the Earth. He saw phases of Venus, which only made sense if Venus was orbiting the Sun. He published his findings, defended them publicly, and the Catholic Church put him on trial and forced him to recant. He spent the last years of his life under house arrest. The truth did not care. The Earth kept orbiting the Sun whether anyone believed it or not. That shift from geocentrism to heliocentrism was one of the most important intellectual revolutions in history. It was the moment we began to understand that we are not special by location. We do not sit at the centre of anything. We are one planet among many, orbiting one star among hundreds of billions, in one galaxy among trillions. Every layer of motion we have discovered since then has reinforced that lesson. We are not still, we are not central. We are passengers on a rock hurtling through a universe that does not notice us. But here is the thing. Even after Copernicus and Galileo, even after we accepted that the Earth moves, most people still assumed the universe itself was static. Stars might move locally, sure, but the cosmos as a whole was thought to be eternal and unchanging. Galaxies, which we did not even know were galaxies until the 1920s, were assumed to be scattered through space in a more or less permanent arrangement. The idea that the whole universe was moving, expanding, evolving, that everything was in motion at every scale, did not become clear until the 20th century, and once it did, it broke cosmology wide open. What we have learned since then is that motion is not incidental to the universe. It is fundamental. Nothing is still. Nothing has ever been still. From the smallest quantum fluctuations to the largest superclusters of galaxies, everything is moving, shifting, falling, expanding, colliding. The universe is not a photograph. It is a film. And we are inside it, moving through it, unable to pause or step outside or see the whole picture at once. The motion we are caught up in is not chaotic. That is the part that keeps scientists awake at night. If galaxies were just drifting randomly through space, their velocities would be scattered in every direction with no pattern. They are not. Galaxies are organized into groups, clusters, and superclusters, and those structures are moving together in enormous streams and flows, as if space itself has currents. The Milky Way is part of one of those currents. We are not wandering, we are being carried. For a long time, astronomers did not have the tools to map those currents. You can measure the motion of nearby galaxies fairly easily by looking at how their light is shifted toward the red or blue end of the spectrum, a phenomenon called redshift and blue shift. If a galaxy is moving toward you, its light gets compressed, shifting toward blue. If it is moving away, the light stretches, shifting toward red. Measure enough galaxies and you can start to piece together a velocity map of the local universe. But that only works out to a certain distance. Beyond a few 100 million light-years, the expansion of the universe itself starts to dominate the signal, and individual motions get washed out. What researchers have discovered by mapping those motions is that galaxies are not spreading out evenly in all directions, they are flowing. Whole clusters of galaxies are moving together in the same direction, as if they are being pulled by something. Some of those flows are easy to explain. Galaxies attract each other. Gravity pulls them together into clusters, and clusters pull on each other. But some of the flows are harder to explain because they seem to be driven by mass concentrations that we cannot see. Regions of space where there should be enormous amounts of matter based on the gravitational pull they exert, but where we do not see enough galaxies to account for it. Astronomers have names for some of those regions: the Great Attractor, the Shapley concentration, names that sound like science fiction but refer to real structures mapped from the motion of thousands of galaxies. We are falling toward them, right now, and we have been falling for billions of years. The motion did not start yesterday. It is not new. It is older than the solar system, older than the sun, older than the rocky planets and the gas giants and every moon and asteroid that ever formed in our neighbourhood. The velocity we are carrying was imparted to us by the structure of the universe itself, by the distribution of matter in the moments after the Big Bang, when tiny fluctuations in density began to collapse under their own gravity and grow into the galaxies and clusters we see today. Stephen Hawking once said that we ourselves are a mere collection of fundamental particles of the universe. That is not poetry. That is physics. Every atom in your body was forged inside a star. Every motion you are part of, from the spin of the Earth to the flight of the Milky Way through intergalactic space, is a consequence of forces and structures that existed long before you did and will continue long after you're gone. You're not separate from the cosmic dance. You are part of it. You have always been part of it. And you will remain part of it until the particles that make you up are scattered across the universe by heat death, or swallowed by black holes, or recycled into new stars billions of years from now. The motion we are caught up in is not something we can escape. There is no neutral ground in space, no place where you could stand still and watch everything else go by. Motion is relative. You're always moving relative to something. The question is not whether we are moving. The question is what we are moving toward. And that question, as it turns out, has an answer that gets stranger the more carefully you look at it. We are not alone in this motion. The Milky Way is part of a collection of galaxies, a neighbourhood bound together by gravity, moving together through space like a fleet. Understanding that neighbourhood, mapping its members, tracing the invisible threads of gravity that hold it together, that is where the story goes next. We are not alone out here. That needs to be said clearly, because when you look up at the night sky and see the pale smudge of the Andromeda galaxy, it is easy to think of it as distant, separate, something over there while we are over here. That is not how gravity works. Andromeda is not a neighbour, in the sense that it lives on the other side of the street. It is a neighbour in the sense that it shares the same driveway, uses the same mailbox, and is currently walking toward your front door with a battering ram. The Milky Way does not drift through empty space in isolation. We are part of a family. Astronomers call it the local group, and it is the gravitational neighbourhood we have been stuck in for billions of years. The local group is a collection of more than 80 galaxies bound together by mutual gravity, occupying a volume of space roughly 10 million light-years across. That sounds enormous, until you remember that the observable universe spans 93 billion light-years. In cosmic terms, the local group is a small town, and like any small town, everyone knows everyone. Everyone is related to someone, and nobody is leaving anytime soon. The three largest members of the local group are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. These are the heavyweights. The Milky Way contains somewhere between 200 and 400 billion stars, depending on whose estimate you trust. Andromeda is larger, probably closer to 1 trillion stars, maybe more. Triangulum is the runt of the big three, weighing in at maybe 40 billion stars, but it is still a proper spiral galaxy with arms and star formation regions, and all the features you would expect from something that deserves to be called a galaxy rather than a smudge. Everything else in the local group is smaller, much smaller. We are talking about dwarf galaxies. The Large Magellanic Cloud and the Small Magellanic Cloud are the two most famous, visible to the naked eye from the southern hemisphere, as faint patches of light that early navigators used for orientation. They orbit the Milky Way like moons, slowly being stripped of gas and stars by our galaxy's gravitational pull. There are dozens of other dwarfs scattered around us. Sculptor, Fornax, Leo 1, Leo 2, Draco, Ursa Minor. Most of them contain only a few million stars, sometimes fewer. Some are so faint that we only discovered them in the last 20 years, when digital sky surveys finally had the sensitivity to pick them out against the background glow of the Milky Way. These dwarf galaxies matter more than their size suggests. They are fossils. Most of them stopped forming new stars billions of years ago, which means they preserve a record of what the early universe looked like before heavier elements were common. Studying their chemistry and structure gives astronomers clues about how galaxies assembled in the first place, how dark matter shaped their formation, and how they survived in an environment dominated by much larger gravitational bullies like the Milky Way and Andromeda. But the real story, the one that defines the local group, is not about the dwarfs. It is about the two giants and what they are doing to each other. The Milky Way and Andromeda are on a collision course, not metaphorically, not eventually, right now, this moment. The distance between the two galaxies is shrinking at roughly 250,000 miles per hour. That is about 110 kilometers per second if you prefer metric. Either way, it is fast. Not fast by the standards of cosmic expansion, where distant galaxies recede from us at speeds that can exceed the speed of light due to the stretching of space itself, but fast by the standards of objects moving through space under their own momentum. Andromeda is currently about 2.5 million light-years away. A light-year is the distance light travels in 1 year, roughly 6 trillion miles. Multiply that by 2.5 million, and you get a number so large it stops meaning anything. 15 quintillion miles, 15 followed by 18 zeros. You cannot visualize that. Nobody can. The human brain did not evolve to process distances like that. What you can understand is that Andromeda is far enough away that the light you see from it tonight left that galaxy 2.5 million years ago, when our ancestors were still figuring out how to chip stones into tools, and it is getting closer. Every second that passes, Andromeda closes the gap by about 70 miles. Every hour it gets closer by 250,000 miles. Every year, closer by more than 2 billion miles. That adds up. Run the clock forward and the math is unavoidable. In roughly 4 to 5 billion years, depending on the model you use and the assumptions you make about the mass distribution of both galaxies, the Milky Way and Andromeda will collide. The word collide is misleading. When galaxies collide, stars do not smash into each other like billiard balls. Space is too empty for that. The distances between stars within a galaxy are enormous compared to the size of the stars themselves. If you scaled the Sun down to the size of a grain of sand, the nearest star would be about 4 miles away. A galaxy is mostly nothing. 2 galaxies passing through each other is more like 2 clouds of gnats interpenetrating. Individual stars will sail past each other without coming anywhere close to touching. But gravity does not care about empty space. Gravity reaches across the void and pulls. When 2 galaxies get close enough, their gravitational fields start to interfere. Stars that were moving in stable orbits around their galactic centers suddenly feel a tug from the other galaxy. Orbits destabilize. Some stars get flung outward into intergalactic space, exiled forever. Others fall inward, sinking toward the center of the merged system. The smooth spiral arms that took billions of years to form get shredded, stretched into long tidal tails that stream away from the collision site like hair in the wind. Simulations of the Milky Way. Andromeda collision have been run hundreds of times by different research groups using increasingly sophisticated models. The details vary, but the broad outline is always the same. The 2 galaxies will approach each other over the course of billions of years, their mutual gravity pulling them together faster and faster. The first pass will be dramatic, but not final. The galaxies will swing past each other, their shapes warping, their spiral arms peeling away, stars and gas sloshing back and forth like water in a bathtub. Then they will separate again, moving apart for a few 100 million years before gravity pulls them back for a second pass. The second pass will be closer, more violent. By this point, both galaxies will have lost their original structure. The Milky Way will no longer look like a spiral. Andromeda will no longer look like a spiral. They will both be mangled, distorted, bleeding stars and gas into the space between them. And then they will fall together a third time. And this time, they will not separate. The cores of the 2 galaxies will merge. The supermassive black holes at their centers, Sagittarius a star in the Milky Way, and the even larger black hole at the heart of Andromeda, will spiral inward and eventually merge into a single monstrous black hole, weighing more than 100 million times the mass of the Sun. The whole process will take about 2 billion years from the first pass to the final merger. By the time it is over, the Milky Way and Andromeda will have become one galaxy. Astronomers have already given it a name, Milkomeda. Some call it Milkdromeda. Either way, it will be a giant elliptical galaxy, a bloated sphere of old stars with no spiral arms, no active star formation, just a slow decline into senescence as the gas needed to make new stars is exhausted or blown away. If Earth still exists at that point, which is not guaranteed, the night sky will look nothing like the sky we see today. Right now, Andromeda appears as a faint smudge to the naked eye, visible only from dark sites far from city lights. It spans roughly 6 times the width of the full moon on the sky, but it is so dim that most people never notice it. As Andromeda gets closer, it will grow larger and brighter. 1 billion years from now, it will dominate the northern sky, a sprawling glow covering a huge swath of the heavens. 2 billion years from now, during the first close pass, the sky will be chaos. Andromeda will no longer look like a galaxy. It will look like a wall of stars stretched and distorted by tidal forces, looming overhead like a frozen tsunami. The Milky Way itself will be visible as a bright band arcing across the sky in directions that make no sense, because our solar system will no longer be in a stable orbit. We will be tumbling through a war zone of gravity and motion, carried along by forces beyond our control. And then there is the Sun. The Sun, by the time the Milky Way and Andromeda finally merge, will be near the end of its life. Main sequence stars like the Sun burn hydrogen into helium for about 10 billion years. The Sun is currently about 4.5 billion years old, which means it has another 5.5 billion years left. By the time Milkomeda is fully formed, the Sun will be running out of hydrogen. It will start burning helium, swell into a red giant, and eventually shed its outer layers into space, leaving behind a white dwarf core no larger than Earth. The Earth itself will either be swallowed by the expanding Sun or baked into a lifeless cinder. Either way, humanity will not be around to see the final sky of the merged galaxy. Not unless we leave. Not unless we find a way to move ourselves to another star, another system, another galaxy entirely. That is the fate of the local group. Merger. Consolidation. The end of the Milky Way as a distinct object. But that fate is still billions of years away, and in the meantime, the local group is not static. The galaxies are moving. The smaller dwarfs are orbiting the larger spirals, slowly losing mass to tidal stripping. The Triangulum galaxy, which orbits Andromeda, may get caught up in the collision as well. Some simulations suggest Triangulum will be torn apart during the merger, its stars scattered into the growing halo of Milkomeda. Other simulations suggest it will survive, ejected from the local group entirely, left to wander alone through intergalactic space. The gravitational forces that govern the local group are surprisingly simple. Newton figured them out in the 1600s. Every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. That is it. That is the equation that determines whether a dwarf galaxy stays bound to the Milky Way or drifts away. That is the equation that ensures Andromeda and the Milky Way will collide. Gravity is not complicated. It is just relentless. It does not care about what you want or what seems fair. It pulls and everything falls. The total mass of the local group is harder to measure than you would think. You cannot just count the stars. Most of the mass in the local group is not in stars. It is in dark matter, the invisible substance that makes up roughly 85% of the matter in the universe. We know dark matter exists because galaxies rotate too fast. The stars at the edge of a galaxy are moving so quickly that they should fly off into space unless there is extra mass holding them in. That extra mass does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. We call it dark matter because we do not know what else to call it. The local group contains roughly 2 trillion solar masses of material, most of it dark matter, distributed unevenly between the Milky Way, Andromeda, and everything else. Andromeda is the heavyweight. Estimates suggest it is about twice as massive as the Milky Way, maybe more. That mass difference is one reason Andromeda is pulling us toward it rather than the other way around. We are not on equal footing. Andromeda is the larger partner in this relationship, and it is dictating the terms of the merger. But the local group itself is not the end of the story. The Milky Way is moving, Andromeda is moving, the entire local group is moving as a unit through space at hundreds of kilometers per second. That motion is not random. It is being driven by something outside the local group, something much larger. To understand what is pulling us, you have to zoom out. You have to look beyond our immediate neighborhood and see the local group not as a destination but as a waypoint, a small structure embedded in a much larger flow. The galaxies in the local group are not expanding away from each other the way distant galaxies are. The expansion of the universe is happening everywhere, but on small scales gravity wins. The local group is gravitationally bound. That phrase means something specific. It means the mutual gravity of the galaxies is strong enough to overcome the expansion of space. We are stuck together. The distance between the Milky Way and Andromeda is not increasing due to cosmic expansion. It is decreasing due to gravity. The same is true for all the dwarf galaxies orbiting the Milky Way and Andromeda. They are bound, they are family, and family does not drift apart, at least not on cosmic timescales. Outside the local group, though, the rules change. A few million light-years away, galaxies are receding from us, carried along by the expansion of the universe. The further away they are, the faster they recede. That is Hubble's law, one of the foundational discoveries of 20th century cosmology. But even that expansion is not uniform. Galaxies are not scattered randomly through space. They clump together into groups, clusters, and superclusters, and those structures have their own internal motions driven by gravity. The local group is part of a much larger structure, a supercluster, and that supercluster is moving. We are moving with it, falling together towards something vast and unseen, a concentration of mass so large that it pulls on everything within hundreds of millions of light years. The collision with Andromeda is the most dramatic event in the local group's future, but it is not the only motion that matters. The local group itself is being carried. We are passengers on a ship, and the ship is heading somewhere. To understand where, you have to pull back the lens and see the local group in context, embedded in a river of galaxies all flowing in the same direction, drawn by the same invisible hand. That river has a name. That structure has been mapped. And what astronomers found when they traced the flow is that the local group is only a small eddy in a current that stretches across 500 million light-years of space. The local group is not the end of the neighbourhood. It is barely the beginning. Zoom out far enough and the Milky Way, Andromeda, all 80+ galaxies in our immediate family, they shrink into a single dot, a pixel in a much larger image. And that image, when you finally pull back far enough to see it whole, reveals something that nobody expected when they started mapping galaxy positions in the 20th century. The universe is not scattered randomly. Galaxies are not sprinkled through space like salt on a table. They are organised. They clump together into groups. Groups cluster into larger structures, and those larger structures connect to each other in a pattern so vast and so intricate that when astronomers first glimpsed it, they had to invent new words just to describe what they were looking at. We call those structures superclusters, and the one we live in, the structure that contains the local group along with thousands of other galaxies, has a name that sounds like it belongs in a fantasy novel. Laniakea. It is a Hawaiian word. It means immeasurable heaven. The astronomers who discovered it in 2014 chose the name deliberately because they were trying to communicate scale. Laniakea is not a building, it is not a city, it is not even a country. It is a region of space 520 million light-years across, containing the mass of roughly 100,000 galaxies like the Milky Way, all of them moving together in a coordinated flow toward a common gravitational centre. 520 million light-years. Let that sit for a second. Light, the fastest thing in the universe, travelling at 186,000 miles per second, would take 520 million years to cross Laniakea from one end to the other. The entire history of complex life on Earth, from the first multicellular organisms in the Precambrian seas to the moment you started reading this sentence, spans about 600 million years. Laniakea is almost that old in light travel time. If a photon left one edge of the supercluster the moment the first animals appeared on Earth, it would just now be arriving at the opposite edge, assuming it did not get absorbed by dust or gas along the way. And we are inside it. Not at the centre, not anywhere special. Just one galaxy and one group in one small corner of a structure so large that for most of human history we did not even know it existed. The Milky Way sits roughly halfway between the centre of Laniakea and its outer edge, moving through space along with everything else in our neighbourhood, all of us caught up in the same gravitational current, flowing like water toward a drain. To understand what Laniakea is, you have to understand what a supercluster is, and to understand that, you have to start smaller. With clusters, a galaxy cluster is a collection of galaxies bound together by gravity. They are the largest gravitationally bound structures in the universe. Clusters can contain anywhere from a few dozen to a few thousand galaxies, all orbiting a common centre of mass, held together by their mutual attraction. The space between the galaxies in a cluster is not empty. It is filled with hot gas, superheated to millions of degrees by the gravitational energy of the cluster itself. That gas glows in X-rays. We cannot see it with our eyes, but X-ray telescopes like Chandra and XMM Newton can, and what they show is that clusters are not just collections of galaxies, they are cauldrons. The gas in a cluster outweighs all the stars in all the galaxies combined. Most of the normal matter in a cluster, the stuff made of protons and neutrons and electrons, is not in stars. It is in the space between them, glowing hot, invisible to the naked eye. The nearest large galaxy cluster to us is called the Virgo cluster. It sits about 54 million light-years away and contains more than 1,000 galaxies. The local group is not part of the Virgo cluster. We are too far away, moving too fast in the wrong direction, but we are being pulled toward it, slowly. The Virgo cluster is massive enough that its gravity reaches across tens of millions of light-years and tugs on everything around it, including us. The Milky Way is falling toward a Virgo at roughly 250 kilometers per second. That is on top of all the other motions we are already participating in. It is another layer of the cosmic conveyor belt, another current pulling us somewhere we did not choose to go. Superclusters are bigger, much bigger. A supercluster is not a single gravitationally bound object. It is a collection of galaxy groups and clusters that occupy the same region of space and share a common motion. The boundaries are fuzzy because superclusters are not held together by gravity in the way clusters are. They are more like watersheds. Imagine a landscape of hills and valleys. Water falling anywhere in a given valley will eventually flow downhill toward the lowest point. Superclusters are like that. Galaxies within a supercluster are all moving under the influence of gravity toward a common basin. They may never actually arrive. The expansion of the universe, which we will get to later, is pulling space apart faster than gravity can pull everything together. But the motion is real. The flow is real. And by mapping that flow, astronomers can define where one supercluster ends and another begins. Laniakea was discovered by a team led by Brent Tully, an astronomer at the University of Hawaii, using a technique that sounds simple but required decades of data to pull off. They measured the velocities of galaxies, not just how fast galaxies are moving away from us due to cosmic expansion, which is easy to measure using redshift, but how fast they are moving through space relative to the expansion. That second number is called peculiar velocity, and it is much harder to pin down because it requires knowing both the distance to a galaxy and its redshift with high precision. Small errors in either measurement blow up into large errors in the calculated velocity. Tully and his team collected distance and velocity measurements for more than 8,000 galaxies within a few hundred million light-years of the Milky Way. Then they used those measurements to build a map. Not a map of where galaxies are, but a map of where they are going. They traced the flow lines, they followed the currents, and what they found was that galaxies are not moving randomly. They are organized into streams, rivers of motion converging on dense regions and flowing away from empty ones. Laniakea emerged from that map as a distinct basin of attraction, a region where all the galaxies are flowing inward toward a common center. That center is not a single object. It is a region, a gravitational low point defined by the combined mass of everything in the area. Tully called it the Great Attractor, a name borrowed from an earlier discovery we will come back to shortly. The map of Laniakea looks like a spider web, or veins, or tree branches. Depending on your metaphor, you can see it as a network of filaments connecting dense nodes where clusters sit, surrounded by vast empty regions called voids, where almost nothing exists. This is the cosmic web, the large-scale structure of the universe, and it is one of the most important discoveries in cosmology. Galaxies are not scattered evenly through space. They are concentrated along filaments, thin threads of matter stretching across hundreds of millions of light-years. Where filaments intersect, you get clusters. Where clusters gather, you get superclusters. And in between, you get voids, enormous bubbles of near emptiness where galaxies are rare and the density of matter is a fraction of the cosmic average. The cosmic web is not random. It is the result of gravity amplifying tiny fluctuations in the density of matter that existed in the very early universe. In the first few 100,000 years after the Big Bang, matter was distributed almost perfectly evenly. Almost. There were tiny variations, regions where the density was slightly higher or slightly lower than average. Those variations were tiny, less than 1 part in 100,000. But gravity does not care how small a difference is. Gravity amplifies. Regions that were slightly denser had slightly stronger gravity. That extra gravity pulled in more matter from the surroundings. The denser regions got denser. The less dense regions got emptier. Over billions of years, those tiny fluctuations grew into the cosmic web we see today. The densest regions collapsed into galaxy clusters. The filaments connecting them became highways of matter. The voids expanded as everything inside them got pulled toward the nearest filament or cluster. Dark matter drove the whole process. Dark matter does not interact with light. It does not emit, absorb, or scatter photons. It does not collide with itself or with ordinary matter except through gravity. That makes it invisible, but it also makes it incredibly important for structure formation because dark matter is not slowed down by pressure or radiation, or any of the forces that complicate the behavior of ordinary matter. Dark matter just falls. It collapses under its own gravity, pulling ordinary matter along with it. The cosmic web is fundamentally a dark matter structure. The galaxies, the stars, the gas, all the stuff we can see, that is just decoration. The scaffolding underneath, the framework that determines where galaxies form and how they move, is made of dark matter. Laniakea contains roughly 100 quadrillion times the mass of the Sun. Most of that mass is dark matter. The galaxies themselves, all 100,000 of them, account for only a small fraction of the total. If you could somehow turn off the light from every star in Laniakea, you would not see much. A few faint glows from hot gas in galaxy clusters, a scattering of dim radio sources, but the structure would still be there. The dark matter halo defining the shape and extent of Laniakea would remain, invisible but real, pulling everything inside it toward the center. The Milky Way is not moving randomly within Laniakea. None of the galaxies are. We're all part of the flow carried along by the gravitational tides generated by the distribution of mass around us. The local group is falling toward the Virgo cluster. The Virgo cluster is falling toward a denser region further away. That denser region is falling toward something even larger. It is currents within currents, flows nested inside flows, all of it moving in a coordinated dance choreographed by gravity and dark matter. One of the strange things about Laniakea is that its boundary is not physical. There is no wall marking the edge of the supercluster. No signpost announcing that you have left Laniakea and entered the neighbouring structure. The boundary is defined by motion. It is the line where the flow changes direction. On one side of the boundary, galaxies are moving inward toward the centre of Laniakea. On the other side, galaxies are moving toward a different basin of attraction, a different supercluster. Cartographers call this kind of boundary a watershed divide. In geography, it is the ridge between two valleys where water falling on one side flows to one river, and water falling on the other side flows to a different river. In cosmology, the equivalent is the surface separating two superclusters, where galaxies on one side flow toward one centre, and galaxies on the other side flow toward another. Laniakea has neighbours. The nearest large supercluster is called Perseus Pisces, sitting beyond Laniakea's boundary in the opposite direction from the Great Attractor. Further out there are others: Coma, Shapley, Hydra Centaurus. Each one is a separate basin of attraction with its own flow pattern, its own centre, its own collection of clusters and groups. The cosmic web is made of these structures, repeated across billions of light years, each one unique in detail, but similar in broad outline. And all of them are moving, not just internally, with galaxies flowing toward their respective centres, but as whole units through space, carried along by even larger scale structures that we are only beginning to map. The discovery of Laniakea changed how astronomers think about our place in the universe. For a long time, the Milky Way's cosmic address was simple. We are in the local group. The local group is near the Virgo cluster. Done. But that picture was incomplete. It described where we are, but it did not describe what we are part of. Laniakea is the larger structure. It is the watershed we live in. The Virgo cluster is not some distant object we happen to be near. It is part of the same flow we are caught up in. We are not falling toward Virgo because it is close. We are falling toward Virgo because Virgo is part of the same gravitational basin we are. It is downstream, closer to the centre, pulling everything around it inward. Brent Tully, the astronomer who led the team that mapped Laniakea, described the discovery in a 2014 paper published in Nature. The title was straightforward: The Laniakea Supercluster of Galaxies. The abstract was blunt. We define a supercluster to be the volume within a surface of a peculiar velocity divergence. Laniakea contains the Milky Way and approximately 100,000 large galaxies. The paper included a three-dimensional map showing the flow lines of galaxies within and around Laniakea, colour-coded by direction and speed. It looks like a river delta seen from above, branching and converging, with the Milky Way sitting in one of the smaller tributaries, carried along by the current. The map is based on distance measurements to thousands of galaxies, most of them collected using a method called the Tully-Fisher relation. The Tully-Fisher relation is an empirical rule linking a spiral galaxy's rotation speed to its intrinsic brightness. Measure how fast a galaxy is spinning, and you can estimate how bright it actually is. Compare that to how bright it appears, and you can calculate how far away it is. It is not perfect. The scatter in the relation introduces errors, but averaged over thousands of galaxies, the method works well enough to map large-scale structure. Tully has spent decades refining the technique and building the catalogue of galaxy distances needed to make a map like this. The flow toward the Great Attractor is one of the most prominent features of the map. The Great Attractor is not a single object. It is a region of overdensity, a concentration of mass sitting near the centre of Laniakea. Galaxies across hundreds of millions of light-years are flowing toward it, pulled by its gravity. The Milky Way is moving toward it at about 600 kilometers per second. That is fast. Faster than our motion toward Andromeda. Faster than our orbit around the center of the Milky Way when you subtract the rotation of the galaxy and isolate the net motion of the local group through space. The Great Attractor is pulling hard, and it has been pulling for billions of years. But here is the odd part. We cannot see the Great Attractor directly. It sits behind the plane of the Milky Way, obscured by the dust and stars of our own galaxy. Astronomers call this region the zone of avoidance because surveys of the extragalactic universe have a blind spot there. Anything sitting behind the Milky Way's disk is hidden. We know the Great Attractor is there because we can measure its gravitational effect on everything around it. We can map the flow of galaxies toward it. We can estimate its mass based on how strongly it pulls. But the object itself, or more accurately, the collection of clusters and groups that make up the overdensity, remains partially hidden. Recent observations, particularly in the infrared and radio wavelengths where dust is less of a problem, have started to pierce the zone of avoidance. What they have found is a massive concentration of galaxies in the direction of the Great Attractor, including a structure called the Norma Cluster, which may be one of the main contributors to the gravitational pull we are feeling. But the full picture is still unclear. The Great Attractor is not a mystery in the sense that we do not understand what it is. It is a concentration of mass. Dark matter, galaxies, clusters, the usual ingredients. The mystery is in the details. How massive is it really? What does the distribution of matter look like inside it? And is it the final destination? Or is there something even larger beyond it pulling not just on us, but on the Great Attractor itself? The answer to that last question is yes, there is something larger. The Shapley concentration, also called the Shapley supercluster, is an even more massive structure sitting several hundred million light-years beyond the Great Attractor. It contains more than 8,000 galaxies and weighs as much as tens of thousands of Milky Ways. And it is pulling. The Great Attractor is not the end of the line. It is a waypoint, a dense region within a larger flow that extends far beyond Laniakea. This is where the map starts to get uncomfortable. The motions we are measuring, the flows we are tracing, they do not stop at the edge of Laniakea. They continue outward, connecting our supercluster to others, revealing structures on even larger scales that we are only beginning to understand. The universe, it turns out, is organized all the way up. Groups cluster into clusters. Clusters gather into superclusters. Superclusters connect along filaments that stretch across significant fractions of the observable universe. And all of it is moving, flowing, falling under the influence of gravity and dark matter and the distribution of mass that has been evolving since the first moments after the Big Bang. The role of dark matter in all this cannot be overstated. Without dark matter, there would be no cosmic web. The ordinary matter we see, the atoms that make up stars and gas and planets, does not have enough gravity on its own to pull structures together on these scales. The fluctuations in density in the early universe were too small. Ordinary matter would have collapsed into clumps, sure, but not into the intricate network of filaments and voids we observe. Dark matter provides the extra gravity needed to amplify those tiny fluctuations into the structures we see today. It is the invisible hand shaping the architecture of the universe. We do not know what dark matter is. That is one of the great unsolved problems in physics. We know it exists because we can measure its gravitational effects. We know how much of it there is, roughly 85% of all matter in the universe. We know it does not emit or absorb light, but we do not know what particles it is made of, how those particles interact with each other, or why dark matter exists in the first place. There are theories, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes. None of them have been confirmed. Experiments buried deep underground and mounted on satellites have been searching for dark matter particles for decades. So far, nothing. The universe is made mostly of something we cannot see, cannot touch, and cannot explain. And that something is responsible for every large-scale structure we observe, including the supercluster we live in. Laniakea is our cosmic home in a way the local group is not. The local group is our immediate family. Laniakea is our city. It is the structure that defines our motion through space on the largest scales we can reliably measure. Everything we do, every motion we are part of, happens within the context of Laniakea. The collision with Andromeda, the flow toward Virgo, the steady pull of the Great Attractor, all of it is local motion within a single supercluster. We are not escaping Laniakea. We are flowing deeper into it, pulled by the gravity of everything around us. And that pull is leading somewhere. The Great Attractor is not just a name, it is a destination. A region of space so dense, so massive that it dominates the motion of galaxies across hundreds of millions of light years. What is there? What is pulling us? And what happens when we finally arrive? The Great Attractor is pulling on you. Right now, this moment. It has been pulling on you since before you were born, and it will keep pulling long after you're gone. You cannot feel it. You will never feel it. But the force is real, measurable, and strong enough to drag the entire Milky Way galaxy, along with hundreds of thousands of neighbouring galaxies, toward a point in space that we cannot fully see and do not entirely understand. And the strangest part is that we discovered it by accident. In the 1970s, astronomers thought they had cosmic motion mostly figured out. Galaxies were receding from each other due to the expansion of the universe. That was Hubble's discovery from the 1920s, confirmed and refined over decades. The further away a galaxy, the faster it appeared to be moving away from us. Simple, elegant. A universe expanding uniformly in all directions, with every galaxy drifting away from every other galaxy like raisins in rising bread dough. Except when astronomers started measuring the velocities of nearby galaxies more carefully, they found something that did not fit. Galaxies were not just moving away from us due to expansion. They were also moving through space, drifting in a particular direction, as if something was pulling them. This extra motion, the motion on top of the expansion, is called peculiar velocity. The term sounds dismissive, like astronomers are calling the motion weird or unusual. But peculiar in this context just means specific to the object. It is the galaxy's own motion through space, independent of the stretching of space itself. Every galaxy has a peculiar velocity. Most of them are small, a few hundred kilometers per second at most, random motions left over from gravitational interactions with nearby galaxies, or the slow infall toward a cluster. But in the 1970s, when astronomers mapped the peculiar velocities of galaxies across a large volume of space, they found something troubling. The motions were not random. Galaxies across hundreds of millions of light years were all drifting in the same direction, as if they were caught in a current flowing towards something massive and invisible. The astronomer who first recognized this pattern was named Alan Dressler, and he was part of a collaboration that became known as the Seven Samurai. The name was not meant to sound cool. It was just a nickname for 7 astronomers who worked together in the 1980s to map galaxy distances and velocities across a large portion of the nearby universe. Dressler, along with Sandra Faber, Donald Lyndon Bell, Roberto Turlovich, Roger Davies, David Burstein, and Gary Wegner, spent years collecting data on elliptical galaxies, measuring how fast they were rotating and how bright they appeared. From those measurements, they could calculate distances using a relationship called the fundamental plane, a method similar to the Tully-Fisher relation, but applicable to elliptical rather than spiral galaxies. What they found when they mapped those distances and velocities was unmistakable. Galaxies were flowing, not just in our local neighbourhood, but across vast distances, all moving together in a coordinated stream toward a region of space in the direction of the constellations Hydra and Centaurus. The flow was not fast compared to the speed of light, but it was fast compared to typical galaxy motions. Hundreds of kilometers per second, fast enough that it could not be explained by the gravity of any single galaxy or even any single cluster. Whatever was pulling had to be enormous. The Seven Samurai called it the Great Attractor. The name stuck. It sounds like something out of science fiction, a galactic whirlpool or a cosmic predator lurking in the dark. In reality, the Great Attractor is not an object. It is a region. A concentration of mass sitting somewhere between 150 and 250 million light-years away, dense enough and massive enough to pull on everything around it across distances that make the local group look like a speck. The Milky Way is falling toward it. Andromeda is falling toward it. The entire local group, the Virgo cluster, thousands of galaxies scattered across Laniakea, all of them are moving in the same general direction, tugged by the gravity of whatever sits at the center of that region. The problem, the reason the Great Attractor remained mysterious for so long, is that we cannot see it. Not because it is invisible in the sense that dark matter is invisible. The mass is there, the galaxies are there, the clusters are there. We cannot see it because it is hidden behind the Milky Way. The plane of our own galaxy, The flat disk, where most of the stars and gas and dust are concentrated, cuts across the sky like a band. If you look up on a clear night from a dark site, you can see it with your eyes. The Milky Way stretches from horizon to horizon, a faint glowing river of light. That glow is the combined light of billions of stars too distant and too faint to resolve individually. Beautiful to look at, a nightmare for extragalactic astronomy. The dust and gas in the Milky Way's disk block light from objects behind it. Not completely. Infrared light can get through, radio waves can get through, but visible light, the wavelengths most telescopes were optimized for throughout the 20th century, gets absorbed or scattered. Astronomers call this region the zone of avoidance, a band roughly 20 degrees tall running all the way around the sky, where surveys of distant galaxies have a blind spot. If you're trying to map the large-scale structure of the universe, and a huge chunk of the sky is blocked by your own galaxy, you have a problem. And if the thing you're trying to study happens to sit right in the middle of that blocked region, you have a bigger problem. The Great Attractor sits squarely in the zone of avoidance. The direction we're being pulled toward, the region where the mass concentration should be, is hidden behind the densest part of the Milky Way's disk. For years, astronomers could infer its existence from the motion of galaxies around it, but they could not see it directly. It was like trying to map a whirlpool by watching the motion of debris on the surface of the water without being able to look down and see the drain itself. Over time, technology improved. Infrared telescopes, which can see through dust more easily than optical telescopes, started to map the zone of avoidance. Radio telescopes, which are not affected by dust at all, mapped the distribution of neutral hydrogen gas in galaxies hidden behind the Milky Way. What they found was that the region of the Great Attractor is not empty, it is crowded. There are clusters, there are superclusters. There is a massive concentration of galaxies in the direction of the constellations Norma and Triangulum Australe, part of a larger structure that extends across a huge volume of space. One of the most prominent features is the Norma cluster, a large galaxy cluster sitting roughly 200 million light-years away, right in the heart of the region where the Great Attractor should be. The Norma cluster is massive, containing hundreds of galaxies and enough hot gas to emit a strong X-ray signal, detectable even through the obscuration of the Milky Way's disk. But the Norma cluster alone is not massive enough to explain the flow. The velocities are too large, the volume of space affected is too big. Whatever the Great Attractor is, it is not a single cluster. It is a collection of clusters and groups, a concentration of mass distributed across a region tens of millions of light-years wide, acting together as a single gravitational basin pulling everything around it inward. And we are one of the things being pulled. The speed at which we are moving toward the Great Attractor depends on how you measure it. If you isolate the peculiar velocity of the local group, subtracting out the expansion of the universe and the rotation of the Milky Way and all the other motions we are participating in, you get a number somewhere around 600 kilometers per second. That is roughly 2.2 million kilometers per hour. 1.4 million miles per hour. Fast. Faster than our motion toward Andromeda. Faster than the Sun's orbit around the galactic center when you account for the net drift of the local group through space. The Great Attractor is pulling hard, and it has been pulling for a long time. 600 kilometers per second is not fast enough to cover the distance to the Great Attractor in anything resembling a human timescale. At that speed, it would take roughly 250 million years to travel 150 million light-years, and that is ignoring the expansion of the universe, which is stretching space and making the journey longer than it would be in a static universe. We are not going to arrive at the Great Attractor, not in any meaningful sense. The expansion of the universe is pulling space apart faster than our peculiar velocity can carry us inward. We are falling, but we are falling through a river that is itself flowing away from the destination. The result is that the distance between us and the Great Attractor is not shrinking. It is growing. Slowly, but growing. We are being pulled, but we are not getting closer. That is one of the strange consequences of living in an expanding universe. Motion and distance do not behave the way intuition says they should, but the pull is real. The force is real. And the fact that we are moving toward the Great Attractor at all, despite the expansion of space trying to carry us apart, tells us that the mass concentration in that region is enormous. Gravity has to be strong enough to overcome the local expansion, to pull galaxies together faster than space is pulling them apart. That requires a lot of mass. Estimates of the Great Attractor's mass vary depending on the model and the assumptions, but most place it somewhere between 10 to the power of 15 and 10 to the power of 16 solar masses. That is 1,000,000 trillion to 10,000,000 trillion times the mass of the Sun. Numbers that large stop meaning anything. The human brain cannot process them. What you can understand is that the Great Attractor is one of the most massive structures in the nearby universe, and its gravity dominates the motion of galaxies across hundreds of millions of light years. But here is where the story gets more complicated. The Great Attractor is not alone, there is something beyond it, something larger. In the 1980s, around the same time the Seven Samurai were mapping the flow toward the Great Attractor, other astronomers were studying a different region of sky. Roughly 600 million light-years away, in the direction of the constellation Centaurus, there is an enormous concentration of galaxies called the Shapley supercluster. It is named after Harlow Shapley, the astronomer who first catalogued many of the clusters in that region in the 1930s. Shapley did not know what he was looking at. He thought he was mapping individual clusters scattered across the sky. It was not until decades later, when redshift surveys allowed astronomers to measure distances accurately, that they realized all those clusters were part of a single massive structure. The Shapley supercluster, also called the Shapley concentration, is the largest concentration of matter in the nearby universe. It contains more than 8,000 galaxies spread across dozens of clusters, with a total mass estimated at roughly 10 to the power of 16 solar masses, possibly more. That makes it significantly more massive than the Great Attractor, and it is pulling. The Shapley concentration is so massive that its gravity reaches across hundreds of millions of light years, affecting the motion of galaxies far beyond its immediate neighbourhood. Some models suggest that the flow we observe toward the Great Attractor is not driven by the Great Attractor alone. It is driven by the combined pull of both the Great Attractor and the Shapley concentration, with Shapley being the larger and more distant contributor. Think of it like a river. You're in a boat drifting downstream. You can see a whirlpool ahead of you, and you are moving toward it. The whirlpool is the Great Attractor, but further downstream past the whirlpool there is a waterfall, a massive drop that is pulling the entire river, including the whirlpool, toward it. The waterfall is Shapley. You are moving toward the whirlpool, yes, but the whirlpool itself is being carried toward the waterfall. The motion you observe is the sum of both effects. That is the picture some cosmologists have proposed for the large-scale flow in our region of the universe. The Great Attractor is real. It is a significant concentration of mass. But it is not the final destination. It is a waypoint, a dense region within a much larger flow driven by the even more massive Shapley concentration sitting beyond it. Measuring these flows is extraordinarily difficult. It requires knowing the distances to thousands of galaxies with high precision, and it requires separating the peculiar velocities from the expansion velocity. Small errors in distance measurements blow up into large errors in calculated velocities. Different surveys, using different methods, sometimes get different answers. Some studies find a strong flow toward Shapley. Others find that the Great Attractor is sufficient to explain most of the observed motion. The debate is not settled. What is settled is that we are moving, and the motion is not random. There is structure to it. There is a cause. Somewhere out there, mass is distributed in a way that generates the flows we observe, and understanding that distribution is one of the key challenges of modern cosmology. The role of dark matter in all this is central. The galaxies we see, the clusters we map, they are only a small fraction of the total mass. Most of the mass driving these flows is dark matter. The Great Attractor is not just a collection of visible galaxies. It is a dark matter halo, a vast concentration of invisible mass that dominates the gravity of the region. The galaxies are embedded in that halo like raisins in a pudding. They trace the distribution of dark matter, but they are not the source of the gravity. The dark matter is, and because dark matter does not emit or absorb light, we cannot map it directly. We can only infer its presence from its gravitational effects, from the way galaxies move, from the way light bends as it passes through the dark matter's gravitational field. One of the tools astronomers use to map dark matter is called gravitational lensing. When light from a distant galaxy passes through a region of space containing a large concentration of mass, the gravity of that mass bends the light, distorting the image of the distant galaxy. The distortion is predictable. By measuring how much the light is bent, you can calculate how much mass is in the foreground, even if that mass is invisible. Gravitational lensing has been used to map the dark matter distribution in galaxy clusters, and it has confirmed what the velocity measurements suggest. The mass is there, the halos are real, and they are much more massive than the visible galaxies alone would indicate. The Great Attractor has been studied with gravitational lensing, though the measurements are difficult because of the zone of avoidance. What the studies have found is consistent with a large dark matter halo centered on the Norma region, extending across tens of millions of light years. The visible galaxies sit at the densest points in the halo, marking where the dark matter concentration is strongest. But the halo itself is much larger than the visible structure, and it is the halo that dominates the gravity. What does it look like? The Great Attractor, I mean. If you could somehow hover above the plane of the Milky Way and look down at the region without any obstruction, what would you see? Not a single object, not a monster. You would see a dense field of galaxies, thousands of them, spread across a volume of space larger than Laniakea. Clusters would stand out as bright knots where galaxies are packed close together, glowing with the combined light of billions of stars. Between the clusters, you would see filaments, streams of galaxies stretched along the edges of voids, connecting the dense regions like bridges. It would look like the cosmic web because it is the cosmic web. The Great Attractor is not a separate thing. It is a dense node in the web, a place where multiple filaments intersect, where the gravity is stronger and the infall of matter is faster. And beyond it, further out, you would see the Shapley concentration. An even denser field of galaxies, an even larger node, pulling everything around it with a gravity so strong that its effects ripple across 500 million light-years of space. That is the structure, that is the machine driving the flow. And we are inside it, caught up in the current, moving through space at speeds we cannot feel, toward destinations we will never reach, carried along by forces we are only beginning to understand. The Great Attractor is not a mystery in the sense that we do not know what it is. It is a mass concentration. Galaxies, clusters, dark matter, the usual ingredients. The mystery is in the scale, in the fact that something so massive and so influential can exist so close to us, and yet remain partially hidden, obscured by the light of our own galaxy. The mystery is in the flows, in the fact that motions on such large scales exist at all, that galaxies hundreds of millions of light-years apart can move together in coordinated streams as if they are connected by invisible threads. The mystery is in the implications. If the Great Attractor and Shapley are driving the motion we observe, what else is out there? What other structures, what other concentrations of mass are pulling on distant galaxies in ways we have not yet measured? The universe is not static. It never was. Every observation we make, every map we draw, reveals more motion, more structure, more complexity. The Great Attractor is one piece of that picture. A large piece, a significant piece, but still just one piece. And the motion it generates is only part of the story. Because while we are falling toward the Great Attractor, while galaxies across Laniakea are streaming toward the dense nodes of the cosmic web, the universe as a whole is doing something else, something that changes everything. It is expanding, not just locally, everywhere. Space itself is stretching, carrying galaxies apart faster than gravity can pull them together. And that expansion, discovered less than a century ago by a man with a telescope pointed at a sky full of galaxies he thought were nebulae, is the next layer of motion we need to talk about. The universe is not static. That sentence seems obvious now, almost trivial. Of course the universe is not static. Everything moves. Galaxies collide, stars explode, black holes swallow matter and spit out jets of radiation. Motion is everywhere. But for most of human history, the idea that the universe as a whole could be changing, that the fabric of space itself could be stretching, carrying galaxies apart like dots on an inflating balloon, was not just wrong, it was unthinkable. The cosmos was eternal, the stars were fixed, the universe might rotate, it might cycle through endless repetitions of creation and destruction, but it did not grow, it did not expand, and it certainly did not have a beginning. That assumption, the static universe, was so deeply embedded in early 20th century physics that even Albert Einstein, the man who revolutionized our understanding of space and time, could not let it go. In 1915, Einstein published his general theory of relativity, a set of equations describing how mass and energy warp the fabric of space-time. The equations were beautiful, they were elegant, they worked. But when Einstein applied them to the universe as a whole, he found something that bothered him. The equations predicted that the universe could not be static. Gravity, acting on all the matter in the cosmos, would pull everything together. The universe should be collapsing. Either that or it should be expanding with the initial outward momentum from some primordial event overcoming the inward pull of gravity. But it could not just sit there, balanced and unchanging, the way everyone assumed it did. Einstein did not like that result. He trusted his equations, but he trusted the prevailing wisdom more. The universe was eternal. The stars were not moving apart. There was no collapse, no expansion, no evidence of anything so dramatic happening on cosmic scales. So Einstein added a term to his equations. He called it the cosmological constant, a kind of repulsive force that would exactly balance gravity on the larger scales, holding the universe in a stable, static equilibrium. It was a fudge factor. Einstein admitted as much later. But at the time, it seemed like the only way to reconcile the math with what everyone believed to be true. He was not alone in that belief. Most astronomers in the early 1900s thought the universe consisted of a single galaxy, the Milky Way, surrounded by empty space that stretched outward forever. The fuzzy patches of light called spiral nebulae, visible through telescopes as faint smudges scattered across the sky, were assumed to be clouds of gas inside the Milky Way, regions where new stars were forming. Nobody thought they were separate galaxies. Nobody thought the universe was big enough to contain more than one. That assumption started to crack in 1923, when Edwin Hubble, working at the Mount Wilson Observatory in California, pointed the most powerful telescope in the world at one of those spiral nebulae and resolved individual stars. The nebula was Andromeda. The telescope was the Hooker telescope, a 100-inch reflector that had just come online a few years earlier. Hubble was looking for Cepheid variable stars, a type of star whose brightness fluctuates in a predictable pattern. The period of the fluctuation, the time it takes for the star to brighten and dim and brighten again, is directly related to the star's intrinsic luminosity. Measure the period, and you know how bright the star actually is. Compare that to how bright it looks from Earth, and you can calculate how far away it is. Hubble found Cepheids in Andromeda. He measured their periods, he did the math, and the distance he calculated was staggering. Andromeda was not a cloud of gas inside the Milky Way. It was nearly 1 million light-years away, far beyond the edge of our galaxy. It was a separate galaxy, a separate island of stars. That discovery, published in 1924, blew the doors off cosmology. If Andromeda was a galaxy, then the other spiral nebulae scattered across the sky were probably galaxies too. The universe was not a single island of stars surrounded by emptiness. It was filled with galaxies, billions of them, stretching outward as far as telescopes could see. The Milky Way was not the cosmos. It was one galaxy among countless others. That shift from a single galaxy universe to a universe full of galaxies was one of the most important conceptual revolutions in the history of science. It changed the scale of everything. It changed what the word universe even meant. But Hubble was not finished. Once he knew that spiral nebulae were galaxies, he started measuring their distances and their velocities. Distance came from Cepheids and other standard candles, objects whose intrinsic brightness is known. Velocity came from spectroscopy, analysing the light from galaxies to see if it was shifted toward the red or blue end of the spectrum. If a galaxy is moving toward you, its light gets compressed, shifting toward blue. If it is moving away, the light gets stretched, shifting toward red. This is the Doppler effect, the same phenomenon that makes an ambulance siren sound higher-pitched as it approaches and lower-pitched as it drives away. With galaxies, the effect shows up in their spectral lines, the dark or bright lines produced by specific elements absorbing or emitting light at precise wavelengths. If those lines are shifted toward the red, the galaxy is moving away. If they are shifted toward the blue, it is moving closer. Hubble measured the redshifts of dozens of galaxies. He plotted them against their distances, and he found a pattern. The further away a galaxy was, the faster it appeared to be moving away from us, not just by a little, by a lot. Close galaxies had small redshifts, meaning they were moving away slowly or not at all. Distant galaxies had large redshifts, meaning they were receding at high speeds, and the relationship was linear. Double the distance, and the recession velocity doubled. Triple the distance, and the velocity tripled. It was a clean, tight correlation. The kind of result that makes a scientist sit up and pay attention, because nature does not produce patterns like that by accident. Hubble published his findings in 1929 in a paper titled A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae. The title is dry, but the implication was anything but. If galaxies are moving away from us, and the further away they are, the faster they are receding, then the universe is expanding. Not expanding into something, not exploding outward from a centre, expanding everywhere at once, with the space between galaxies stretching like the fabric of a balloon being inflated. That is what Hubble's data suggested, and it upended every assumption about the nature of the cosmos. There is a common misconception about this discovery that needs to be cleared up. Hubble is often credited with discovering the expansion of the universe. That is not quite accurate. The expansion was first predicted theoretically by a Belgian priest and physicist named Georges Lemaitre, who published a paper in 1927, 2 years before Hubble's observational work, showing that Einstein's equations naturally led to an expanding universe if you did not artificially hold it static with the cosmological constant. Lemaitre even proposed what he called the primeval atom, the idea that the universe began in a hot, dense state and has been expanding ever since. The paper was published in a Belgian journal and went mostly unnoticed. Hubble, working independently, provided the observational evidence that confirmed what Lemaitre had predicted. The discovery is theirs together, though history has given Hubble most of the credit, partly because his name is attached to the law describing the expansion, and partly because observational proof carries more weight in science than theoretical prediction. The relationship Hubble found, the correlation between distance and recession velocity, became known as Hubble's law. The mathematical form is simple. The recession velocity of a galaxy is equal to its distance multiplied by a constant. That constant, now called the Hubble constant, measures the rate of expansion. The bigger the constant, the faster the universe is expanding. The smaller the constant, the slower the expansion. Hubble's original estimate of the constant was way off. He calculated a value that made the universe appear younger than the Earth, which was obviously wrong. The error came from problems with the distance measurements. Cephids are tricky. There are different types, and if you confuse one type for another, your distance calculations get thrown off. But the relationship itself was real. The universe was expanding. That conclusion held up. Einstein, when he heard about Hubble's discovery, reportedly called the cosmological constant the biggest blunder of his career. If he had trusted his equations instead of trying to force them to match the prevailing belief in a static universe, he could have predicted the expansion before anyone observed it. Instead, he added a fudge factor to make the math agree with what everyone thought was true. The irony is that the cosmological constant turned out to be real after all, but not in the way Einstein originally used it. It reappeared decades later as dark energy, the mysterious force driving the accelerated expansion of the universe. But that is a story for the next chapter. For now, what matters is that the static universe was dead. The cosmos was not eternal and unchanging. It was dynamic, it was growing, and that meant it had a history. If the universe is expanding now, then it was smaller in the past. Run the clock backward, and galaxies get closer together. Keep going, and they merge into a single dense mass. Keep going further, and the matter in the universe gets compressed into a smaller and smaller volume, hotter and denser, until you reach a point where the equations break down and the entire observable universe was packed into a region smaller than an atom. That point, that moment of maximum compression, is what we now call the Big Bang. The name was coined by Fred Hoyle, a British astronomer who did not believe in the theory and meant the term as an insult. It stuck anyway. The Big Bang is not an explosion in space, it is an expansion of space. The universe did not blow apart like a bomb going off. Space itself started expanding, carrying matter along with it, stretching and cooling over billions of years into the galaxies and stars and planets we see today. The expansion of the universe is not intuitive. It does not match anything we experience in daily life. Objects do not spontaneously move apart because the space between them is growing. Your desk does not expand. The Earth does not expand. The solar system does not expand. The Milky Way does not expand. Expansion only matters on the larger scales, where the distances are so vast that the stretching of space adds up to something measurable. Inside gravitationally bound systems like galaxies or clusters or even superclusters, gravity holds everything together. The expansion tries to pull things apart, but gravity wins. It is only on scales larger than superclusters, where gravity is too weak to hold structures together, that the expansion dominates. Cosmologists use analogies to explain this. The most common is the raisin bread analogy. Imagine baking a loaf of raisin bread. As the dough rises, the raisins move apart from each other, not because they're moving through the dough, but because the dough itself is expanding. From the perspective of any single raisin, all the other raisins appear to be moving away. The further away a raisin is, the faster it seems to be receding, because there is more dough between them, and all that dough is expanding. That is how galaxies behave in an expanding universe. They are not flying through space. They are embedded in space, and space is stretching. Another analogy is an inflating balloon. Draw dots on the surface of a deflated balloon, then blow it up. As the balloon inflates, the dots move apart. None of them is at the center. None of them is moving toward an edge. Every dot sees all the other dots receding, and the further away a dot is, the faster it appears to move. The balloon is a two-dimensional surface, and the expansion is happening in all directions on that surface. In the real universe, space is three-dimensional, and the expansion is happening in all three dimensions, but the principle is the same. There is no center. There is no edge. Everything is moving away from everything else because the space between them is growing. The distinction between motion through space and the expansion of space is critical. When we talk about the Milky Way moving toward Andromeda or the local group falling toward the Great Attractor, we're talking about motion through space. Those are peculiar velocities, the result of gravity pulling objects together. When we talk about distant galaxies receding from us at speeds that can exceed the speed of light, we are talking about the expansion of space. The galaxies are not moving through space faster than light. That would violate relativity. They are being carried apart by the stretching of space itself, and there is no speed limit on that. Space can expand as fast as it wants. The recession velocity is not a velocity in the traditional sense. It is a rate of separation driven by the metric of space changing over time. Hubble's law gives us a way to measure that expansion. If you know the Hubble constant, you can calculate how fast a galaxy should be receding based on its distance. If you know the recession velocity, you can calculate the distance. The relationship works both ways. For nearby galaxies within a few 100 million light-years, the expansion is small compared to the peculiar velocities. The motion we observe is mostly due to gravity. But beyond that, once you get out to distances of 1 billion light-years or more, the expansion dominates. The galaxies are receding so fast that their light is stretched into the infrared, or even the radio part of the spectrum. The further away you look, the more redshifted the light becomes, and the faster the galaxy appears to be moving. This has profound implications. One is that the universe has an age. If the expansion has been happening at a more or less constant rate, and you know the Hubble constant, you can calculate how long it has been since everything was compressed into a single point. Run the math, and you get an age of roughly 13.7 to 13.8 billion years. That is the age of the universe, the time since the Big Bang confirmed by multiple independent measurements, including observations of the cosmic microwave background, the ages of the oldest stars, and the distribution of elements forged in the first few minutes after the Big Bang. The universe is not eternal. It had a beginning. And that beginning was not that long ago, at least compared to the infinite stretch of time people once assumed the cosmos had existed. Another implication is that the universe has a size. Not a size in the sense of an edge or a boundary, but a size in the sense that there is a limit to how far we can see. Light travels at a finite speed, and the universe has a finite age, so there is a maximum distance light could have travelled since the Big Bang. That distance, accounting for the expansion of space over time, defines the observable universe, a sphere roughly 93 billion light-years across with Earth at the centre, not because we are special, but because we are the observers. Every observer, no matter where they are in the universe, sees themselves at the centre of their own observable universe. Beyond that horizon, there are galaxies we will never see because their light has not had time to reach us yet, and because of the accelerating expansion, never will. The expansion also explains something that puzzled astronomers for years. If the universe is full of galaxies, and those galaxies are full of stars, and stars shine in all directions, then why is the night sky dark? This is called Olbers' paradox, named after a 19th century astronomer who pointed out that in an infinite, static, eternal universe filled with stars, every line of sight should eventually hit a star, and the sky should be as bright as the surface of the sun. It is not. The sky is dark. The expansion of the universe solves the paradox. The light from distant galaxies is redshifted by the expansion, stretched into wavelengths our eyes cannot see. The further away a galaxy is, the more its light is stretched, and beyond a certain distance the light is redshifted so much that it becomes undetectable. That is why the sky is dark. The expansion dims the light from the most distant sources, leaving only the nearby stars and galaxies bright enough to see. Hubble's revelation was not welcomed by everyone. Plenty of scientists resisted the idea of an expanding universe because it implied a beginning, and a beginning implied something uncomfortably close to creation. The steady-state theory, championed by Fred Hoyle and others, proposed that the universe was expanding but had no beginning. New matter was continuously being created in the voids between galaxies, keeping the overall density constant. As space expanded, new galaxies formed to replace the ones that drifted away. The universe looked the same at all times, eternal and unchanging in the large-scale average even though it was expanding locally. The steady-state model was elegant. It avoided the messy questions of what came before the Big Bang and what caused it. But it made predictions that turned out to be wrong. In the 1960s, the discovery of the cosmic microwave background, the faint glow of radiation left over from the hot early universe, killed the steady-state theory. The Big Bang model predicted that radiation. The steady-state model did not. That was the end of the debate. The universe had a beginning, it started hot and dense and has been expanding and cooling ever since. The expansion is not just a historical fact, it is ongoing. Right now, space is stretching. Galaxies that are not gravitationally bound to us are moving away. The further away they are, the faster they recede. The recession is not something we can feel or measure locally. The Earth is not expanding. The solar system is not expanding. The Milky Way is not expanding. But look beyond the local group, beyond Laniakea, out to galaxies hundreds of millions or billions of light years away, and the expansion is unmistakable. The light from those galaxies arrives redshifted, stretched by the expansion of space during the billions of years it took the light to reach us. And the redshift is increasing. Galaxies that are far away now will be farther away in the future. Their light will be more redshifted. Eventually, if the expansion continues, they will recede so fast that their light will no longer reach us. They will vanish beyond the horizon, lost to observation forever. For decades after Hubble's discovery, astronomers assumed the expansion was slowing down. Gravity, pulling on all the matter in the universe, should act as a brake, decelerating the expansion over time. The question was not whether the expansion would slow. The question was whether it would slow enough to stop, reverse, and collapse back into a big crunch, or whether it would keep expanding forever, gradually slowing but never quite stopping. Those were the two options: deceleration leading to collapse, or deceleration leading to eternal expansion. The fate of the universe hinged on the total amount of matter and energy in the cosmos. If there was enough, gravity would win, and the universe would eventually collapse. If there was not enough, the expansion would continue forever, and the universe would grow cold and dark and empty as stars burned out and galaxies drifted apart. Turns out, both options were wrong. The expansion is not decelerating, it is accelerating. Distant galaxies are receding faster now than they were in the past. Something is pushing space apart, overcoming gravity, driving the expansion to speeds that increase over time. That something is called dark energy, and it makes up roughly 68% of the total energy content of the universe. We do not know what it is. We do not know where it comes from. We do not know why it exists. But we know it is there because we can measure its effects. The universe is not just expanding, it is accelerating, and that changes everything. Edwin Hubble did not live to see that discovery. He died in 1953, long before astronomers had the tools to measure the acceleration. But his work laid the foundation. The expanding universe, the relationship between distance and velocity, the idea that the cosmos has a history and a future that can be predicted from observations, all of that started with Hubble. He proved that the universe is not static. He showed that motion on the largest scales is not just driven by gravity pulling things together. It is driven by space itself stretching and carrying galaxies apart. And that revelation, that shift from a static eternal cosmos to a dynamic expanding universe with a beginning and a fate, is one of the most profound discoveries in the history of science. The implications are still unfolding, and the next layer, the acceleration, the dark energy, the realization that the universe is not just moving but speeding up. That is where the story turns strange. The universe should be slowing down. That was the assumption. It made sense. It was logical. Gravity pulls everything together. The Big Bang threw everything apart, and gravity has been trying to rein it back in ever since. The expansion of the universe, discovered by Hubble in the late 1920s, was supposed to be decelerating, slowing down over time as the mutual gravitational attraction of all the matter in the cosmos gradually applied the brakes. The only question, the only real debate, was whether there was enough matter to stop the expansion completely and reverse it, leading to a big crunch where the universe collapsed back into a hot, dense point, or whether the expansion would continue forever, gradually slowing but never quite stopping, leading to a cold, dark, empty future where galaxies drifted so far apart that the night sky eventually went black. Those were the two options on the table going into the 1990s, deceleration leading to collapse, or deceleration leading to eternal expansion. Both scenarios assumed the same basic physics. Gravity was the only force acting on cosmic scales. Dark matter was already known by then, inferred from the way galaxies rotate and the way clusters hold together. Astronomers knew that most of the matter in the universe was invisible, detectable only through its gravitational effects, but dark matter was still matter. It still had gravity. It still pulled. The expectation was that once you added up all the visible matter and all the dark matter, you would get a number that told you which future the universe was heading toward. Collapse or expansion. Those were the choices. In 1998, two independent teams of astronomers published results that blew both options apart. The universe was not decelerating, it was accelerating. The expansion was speeding up, getting faster over time, as if something was pushing space apart with a force strong enough to overcome the gravity of all the matter in the cosmos. That discovery, announced in papers published just months apart, won the Nobel Prize in Physics in 2011. It was one of the biggest surprises in the history of cosmology, and it introduced a new player into the cosmic drama, a mysterious entity that nobody saw coming and that nobody, even today, fully understands. They called it dark energy. The discovery came from studying supernovae. Not just any supernovae, but a specific type called type Ia. Supernovae are stellar explosions, the violent deaths of stars. There are different kinds depending on what kind of star explodes and how it explodes. Type Ia supernovae are particularly useful for cosmology, because they are what astronomers call standard candles. A standard candle is an object whose intrinsic brightness is known. If you know how bright something actually is, and you can measure how bright it appears from Earth, you can calculate how far away it is. The further away an object is, the dimmer it looks. The relationship is precise. Double the distance, and the brightness drops by a factor of 4. Triple the distance, and the brightness drops by a factor of 9. Measure the brightness, and you get the distance. Type Ia supernovae are standard candles because they explode in a very specific way. They start as white dwarfs, the burned-out cores of stars like the Sun sitting in binary systems where they are slowly pulling matter off a companion star. As the white dwarf accumulates mass, it gets closer and closer to a critical threshold called the Chandrasekhar limit, roughly 1.4 times the mass of the Sun. When the white dwarf hits that limit, the pressure at its core becomes so intense that carbon and oxygen nuclei begin fusing in a runaway chain reaction. The entire star explodes in a matter of seconds, releasing as much energy as the Sun will emit over its entire 10 billion year lifetime. And because all type Ia supernovae explode at the same mass threshold, they all release roughly the same amount of energy, which means they all shine with roughly the same peak brightness. That is what makes them standard candles. See one, measure how bright it looks, and you know how far away it is. In the 1990s, two teams set out to use type Ia supernovae to measure the deceleration of the universe. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees at the Space Telescope Science Institute. High-Z is astronomy shorthand for high redshift, meaning very distant. The goal was to find supernovae in galaxies billions of light years away, measure their brightness and redshift, and use those measurements to determine how much the expansion had slowed down over cosmic time. The method was straightforward in principle. Find distant supernova, Measure how far away they are based on their brightness. Measure how fast they are receding based on their redshift, and compare the two. If the expansion was decelerating, distant supernovae should be closer than you would expect based on their redshift, because in a decelerating universe, galaxies were moving faster in the past than they are now. The expansion has been slowing down, so objects at high redshift, which we see as they were billions of years ago, were receding faster back then than the current expansion rate would predict. That would make them appear slightly closer, slightly brighter than they would be in a universe expanding at a constant rate. That is not what the teams found. The distant supernovae were dimmer than expected. Not by a lot, but by enough that the signal was clear once you averaged over dozens of measurements. Dimmer means further away. Further away means the expansion was slower in the past than the current rate would predict. And if the expansion was slower in the past and faster now, that means the expansion is accelerating. The universe is not coasting, it is speeding up. The result was so unexpected that both teams checked and rechecked their data. They looked for systematic errors. They looked for dust that might be dimming the supernovae and making them appear further away than they actually were. They looked for evolutionary effects, the possibility that supernovae in the distant past were intrinsically different from supernovae today in ways that would throw off the distance measurements. They found nothing. The signal held up. The supernovae were dimmer, the universe was accelerating, and that meant something was pushing space apart, something that did not fit into any of the existing models. They called it dark energy because nobody knew what else to call it. Dark in the sense that it does not emit or absorb light. Energy because it has to contribute to the total energy content of the universe. But beyond that, the name is a placeholder. Dark energy is not a thing. It is a label for an effect. The universe is accelerating. Something must be causing that acceleration. We call that something dark energy. But we do not know what it is, how it works, or why it exists. We only know what it does. It pushes. The amount of dark energy in the universe is staggering. If you add up all the energy in the cosmos, all the matter, all the radiation, all the kinetic energy of moving particles, all the gravitational potential energy of structures bound together by gravity, and convert everything into a single common unit, you find that roughly 68% of the total is dark energy. Not 68% of the matter, 68% of everything. Dark matter, the invisible stuff that dominates the gravity of galaxies and clusters, accounts for about 27%. Ordinary matter, the stuff made of protons and neutrons and electrons, the stuff that makes up stars and planets and people, accounts for less than 5%. We are a rounding error. The universe is dominated by two forms of substance that we cannot see, cannot touch, and do not fully understand. And the larger of the two, dark energy, is not even matter. It is something else entirely. The leading explanation for dark energy is the cosmological constant, the same term Einstein added to his equations in 1915 to keep the universe static. Einstein called it his biggest blunder after Hubble discovered the expansion, but it turns out he was not wrong. He was early. The cosmological constant is a property of space itself, a kind of intrinsic energy density that does not change over time or dilute as the universe expands. In Einstein's general relativity, the cosmological constant is represented by the Greek letter lambda, which is why the current standard model of cosmology is called lambda CDM, where CDM stands for cold dark matter. Lambda is the cosmological constant. CDM is the dark matter. Together they describe a universe dominated by invisible components that shape its evolution on the larger scales. The cosmological constant has a strange property. It has negative pressure. Pressure, in physics, is a force per unit area. Positive pressure pushes outward. Negative pressure pulls inward, but in a way that is deeply counterintuitive. In general relativity, pressure contributes to gravity. Positive pressure makes gravity stronger. Negative pressure makes gravity repulsive. That is not a typo. Negative pressure, which sounds like it should pull things together, actually pushes them apart when you plug it into Einstein's equations. The cosmological constant, as a form of energy with negative pressure, generates a repulsive gravitational effect that drives the accelerated expansion of the universe. Think of it this way. Ordinary matter has positive energy density and negligible pressure. As the universe expands, the density of matter drops. Spread the same amount of matter over a larger volume, and the density goes down. Dark energy, if it is the cosmological constant, has a fixed energy density. It does not dilute. As space expands, the amount of dark energy per unit volume stays the same. That means the total amount of dark energy in the universe increases as the volume increases. More space, more dark energy. And because dark energy has negative pressure, the more of it there is, the stronger the repulsive effect becomes. That is why the expansion is accelerating. Dark energy is winning the tug-of-war with gravity, and the more the universe expands, the more dark energy there is, and the faster the expansion gets. The cosmological constant is the simplest explanation for dark energy. It fits the data. It requires only one number, the energy density of the vacuum, and that number does not change over time. Plug it into the equations, and you get a universe that matches observations. The expansion accelerates. Distant supernovae are dimmer than they would be in a decelerating universe. The cosmic microwave background shows the pattern of fluctuations you would expect if dark energy exists. The large-scale structure of galaxies, the way matter is distributed across billions of light-years, matches what the lambda CDM model predicts. It works, but it has a problem, a big one. The energy density of the vacuum, the value of the cosmological constant, can be calculated from quantum field theory, the branch of physics that describes the behavior of particles and fields at the smallest scales. According to quantum field theory, empty space is not empty. It seethes with virtual particles popping in and out of existence, fluctuations in the quantum fields that fill the universe. Those fluctuations contribute energy to the vacuum, and when you add them all up, you get a number. That number, the predicted energy density of the vacuum based on quantum field theory, is 10 to the power of 120 times larger than the observed value. That is not a typo. 120 orders of magnitude. The prediction is off by a factor of 1 followed by 120 zeros. That discrepancy is called the cosmological constant problem, and it is one of the worst mismatches between theory and observation in the history of physics. If the vacuum energy were as large as quantum field theory predicts, the universe would have blown apart in the first fraction of a second after the Big Bang. Galaxies would not exist, stars would not exist, we would not exist. The fact that the observed value is so much smaller than the predicted value suggests that either quantum field theory is missing something fundamental, or there is some mechanism that cancels out most of the vacuum energy, leaving only a tiny residual amount. Nobody knows what that mechanism is. The cosmological constant works as a description of dark energy. It does not work as an explanation. The alternative to the cosmological constant is a hypothetical field called quintessence. Quintessence is a dynamic form of dark energy, a field that changes over time and varies from place to place, unlike the cosmological constant, which is the same everywhere and always. The name comes from the fifth element, quinta essentia, the substance ancient and medieval philosophers believed filled the heavens beyond the four classical elements of earth, water, air, and fire. Quintessence fields can evolve, which means the strength of dark energy could have been different in the past and could change in the future. That flexibility makes quintessence appealing because it opens up possibilities that the cosmological constant does not allow, but it also makes it harder to test. The cosmological constant has one parameter. Quintessence models have multiple parameters, and different models make different predictions, many of which are hard to distinguish from each other or from the cosmological constant given the current precision of measurements. The data so far favour the cosmological constant. Observations of the cosmic microwave background, the distribution of galaxies, the brightness of distant supernovae, all of them are consistent with dark energy having a constant density over time. There is no strong evidence yet that dark energy is evolving. That could change as measurements get more precise. The European Space Agency's Euclid mission, launched in 2023, and NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, are both designed to measure the properties of dark energy with unprecedented accuracy. They will map the positions and redshifts of billions of galaxies, measuring the expansion rate at different points in cosmic history, with enough precision to detect changes in the strength of dark energy over time, if those changes exist. If dark energy is quintessence, those missions should be able to see it. If it is the cosmological constant, they will confirm that with much higher confidence than we have now. What is clear already is that dark energy dominates the large-scale evolution of the universe. In the early universe, when matter was densely packed, gravity was the dominant force, The expansion was decelerating, slowing down as matter pulled on itself. But as the universe expanded, the density of matter dropped, and the strength of gravity weakened. Dark energy, with its constant energy density, did not weaken. It stayed the same. Eventually, a few billion years ago, dark energy became strong enough to overcome gravity on the larger scales. The expansion stopped decelerating and started accelerating. That transition happened relatively recently in cosmic history, roughly 4 billion years ago based on the most common models. Before that, the universe was slowing down. After that, it started speeding up. We live in the era of acceleration. The consequences of that acceleration are profound. On scales smaller than superclusters, gravity still holds structures together. Galaxies are still colliding. Clusters are still growing. The local group is still falling toward the great attractor. Dark energy does not overpower gravity on those scales, but on larger scales, beyond the gravitationally bound structures, dark energy dominates. Galaxies that are not already bound to us by gravity are moving away, and they are moving away faster as time goes on. The space between them is stretching, and the stretching is accelerating. Eventually, those galaxies will recede so fast that their light will no longer be able to reach us. They will cross the cosmological horizon, the boundary beyond which the expansion is carrying objects away faster than light can travel toward us. Once a galaxy crosses that horizon, it is gone. We will never see it again. Its light will never catch up. It will vanish from the observable universe. The horizon is shrinking, not in distance, but in the number of galaxies inside it. Right now, we can see galaxies out to a distance of roughly 46 billion light-years, accounting for the expansion of space during the time their light has been travelling toward us. That is the edge of the observable universe. But as the expansion accelerates, fewer and fewer galaxies will remain visible. Galaxies that are near the edge of the observable universe now will cross the horizon in the future. Their light will stop reaching us. Billions of years from now, the night sky will contain fewer galaxies. Tens of billions of years from now, only the galaxies in our local supercluster will be visible. Eventually, only the galaxies in the local group will remain, and even some of those might drift away if they are not tightly bound. The universe will look smaller, emptier, lonelier. The accelerated expansion also affects the ultimate fate of the universe. In a decelerating universe, the choice was between collapse and eternal expansion. In an accelerating universe dominated by dark energy, collapse is off the table. The expansion will not reverse. It will not slow down. It will keep accelerating forever unless something changes. The universe is headed toward a future where galaxies are so far apart that they can no longer see each other, where stars burn out and are not replaced because the gas needed to make new stars has been exhausted, where the cosmos grows cold and dark and empty. That future is called the Big Freeze, or sometimes heat death, the state where the universe reaches maximum entropy and nothing interesting can happen anymore. The timeline for the Big Freeze is so long that it makes billions of years look like an eye blink. Stars will keep forming for trillions of years, as long as there is gas to collapse into new suns. The smallest stars, the red dwarfs, burn so slowly that they can last for tens of trillions of years. But eventually the gas runs out, star formation stops, the last stars burn out, galaxies go dark. Black holes slowly evaporate through a process called Hawking radiation, which is so slow that even the largest black holes take 10 to the power of 100 years to disappear. After that, nothing is left but a dilute sea of particles, mostly photons and neutrinos, drifting through an ever-expanding space that grows colder and more empty with every passing eon. That is the endpoint if dark energy continues to dominate. But there is a wrinkle. The cosmological constant, if that is what dark energy is, predicts that the strength of dark energy stays constant forever. The universe accelerates at a steady rate, asymptotically approaching a maximum expansion speed, but never quite reaching it. That is the standard picture. But if dark energy is quintessence, if it can evolve over time, then the future is less certain. Quintessence could weaken, in which case gravity might reassert itself, and the acceleration could slow down or stop. Or quintessence could strengthen, in which case the acceleration could increase, eventually becoming so strong that it tears galaxies apart, then solar systems, then planets, then atoms. That scenario is called the Big Rip, and it is one of the possible endpoints if dark energy is dynamic and grows over time. Current observations do not favour the Big Rip. The data suggests dark energy is not getting stronger, but the possibility is not ruled out. The discovery of dark energy and the accelerated expansion changed the way cosmologists think about the universe. Before 1998, the standard model of cosmology was relatively simple: matter, radiation, and the expansion. Gravity pulling things together, the expansion carrying them apart, the balance between the two determining the fate of the cosmos. After 1998, the model became more complicated. Dark energy, a mysterious component making up more than 2/3 of the universe, driving an accelerated expansion that will continue forever unless something unexpected happens. The universe is not slowing down, it is speeding up, and that changes everything. The measurements that reveal the acceleration are remarkably precise. The Hubble constant, the number that measures the current expansion rate, is known to within a few percent. Different methods give slightly different values, which has led to what astronomers call the Hubble tension, an ongoing debate about whether the discrepancy between measurements is real or the result of unaccounted for errors. Some methods, like observations of the cosmic microwave background, give a value around 67 km per second per megaparsec. Other methods, like direct measurements using supernovae and Cepheid variables, give a value around 73. That 6 km per second difference might not sound like much, but it is statistically significant, and it has persisted despite years of effort to resolve it. If the tension is real, it could indicate that something in the standard model is wrong, or that dark energy is more complicated than the cosmological constant. If it is not real, if the tension is due to unrecognized systematic errors in the measurements, then the standard model is safe. The jury is still out. What is not in doubt is the expansion itself. The universe is getting bigger, space is stretching, galaxies are moving apart, and the rate of separation is increasing over time. That is the reality we live in. A universe dominated by invisible components, dark matter and dark energy, that shape its evolution in ways we're only beginning to understand. The discovery of the accelerated expansion is less than 30 years old. The data are solid, the implications are profound, but the explanation, the underlying physics of what dark energy actually is, remains one of the deepest mysteries in science. The universe is not static. It is not coasting. It is accelerating, driven by a force we cannot see, toward a future we are only starting to map. And that future, the ultimate fate of the cosmos, depends entirely on what dark energy does next. If it stays constant, the universe expands forever, growing cold and empty. If it evolves, if its strength changes over time, then the future could be very different. We do not know which it is, but we are watching, we are measuring, and every observation, every new piece of data, brings us closer to understanding the force that is pushing the universe apart and determining what happens next. The endgame is already written in the equations. We just need to figure out which set of equations is the right one. The universe is going to end. That needs to be said plainly because for most of human history, the idea that the cosmos had a beginning, let alone an ending, was unthinkable. The stars were eternal, the heavens were unchanging, time stretched backward and forward without limit. But we know better now. The universe had a beginning. It started roughly 13.8 billion years ago in a hot, dense state we call the Big Bang. And if it had a beginning, it will have an ending. The details of that ending, the mechanism, the timeline, the final state, those are still being worked out. But the broad strokes are clear. The universe will not last forever in its current form. Eventually the stars will burn out, the galaxies will go dark, the expansion will carry everything so far apart that the cosmos becomes a cold, empty void where nothing interesting can ever happen again. That is the future. Not might be, will be. Unless something changes. Unless dark energy behaves differently than we think. Unless the physics we have mapped so carefully over the last century turns out to be incomplete in some fundamental way. Those are possibilities, but they are not the favoured bet. The most likely outcome, based on everything we have observed, is that the universe is headed toward a long, slow, cold death, and there is nothing we can do to stop it. For a long time, cosmologists debated two possible fates for the universe. Both scenarios assumed the same basic framework. The universe was expanding, gravity was pulling matter together, and the balance between the two would determine the endgame. If there was enough matter, enough gravity, the expansion would eventually slow down, stop, and reverse. The universe would collapse back into a hot, dense point in an event called the Big Crunch. All the galaxies, all the stars, all the atoms scattered across billions of light-years of space would fall back together, crushed into a singularity. Time would end. Space would end. Everything would be compressed back into the same state the universe started in, and maybe, just maybe, the whole thing would bounce and start over in a new Big Bang. That was one option. The other option was that there was not enough matter to stop the expansion. Gravity would slow it down, but not enough. The universe would keep expanding forever, gradually slowing but never quite stopping. Stars would burn out, galaxies would drift apart. The cosmos would grow colder and darker and emptier until it reached a state of maximum entropy, a condition where no energy was available to do work, where nothing could change, where the universe was effectively dead even though it still technically existed. That scenario was called the Big Freeze, or sometimes the Big Chill, or heat death. Both names describe the same end state. A universe that has run out of usable energy and settled into a final equilibrium that lasts forever. Those were the two options, collapse or expansion, Big Crunch or Big Freeze. The question was which one the universe was headed toward, and the answer depended on a single number: the total density of matter and energy in the cosmos. If the density was above a critical threshold, gravity would win and the universe would collapse. If it was below that threshold, expansion would win and the universe would freeze. Throughout the 1980s and early 1990s, astronomers worked to measure that density. They counted galaxies. They measured the mass of clusters. They mapped the distribution of dark matter using gravitational lensing and galaxy rotation curves. And what they found was that the universe was close to the critical density, maybe slightly below it, but not by much. The data suggested the universe was on the edge, teetering between collapse and eternal expansion. That balance was puzzling. Why should the density be so close to critical? Why not much higher or much lower? The universe did not seem to care about human intuition, and the numbers did not offer a clear answer. Then came 1998, the discovery that the expansion was not slowing down. It was speeding up. Distant supernovae were dimmer than they should be, which meant they were further away than expected, which meant the expansion was accelerating. That finding, announced by two independent teams studying Type Ia supernovae in galaxies billions of light-years away, changed everything. Acceleration meant there was something pushing space apart, something with enough strength to overcome the gravity of all the matter in the universe. That something was dark energy, and it made up roughly 68% of the total energy content of the cosmos. Dark energy does not clump. It does not form galaxies or clusters. It does not dilute as space expands. It just sits there, everywhere, pushing, and the more space there is, the more dark energy there is, and the stronger the push becomes. That is why the expansion is accelerating. Dark energy is winning the tug of war with gravity, and the gap is widening. The discovery of dark energy killed the Big Crunch, not immediately. There are still models where dark energy could weaken over time, or reverse sign, turning from a repulsive force into an attractive one, in which case the expansion could slow down, stop, and reverse, leading to a collapse after all. But those models are not favoured by the data. Everything we have observed so far suggests that dark energy is constant or close to it. It is not weakening. It is not changing. The universe is accelerating now, and it will keep accelerating. That means the Big Crunch is off the table. The universe is not going to collapse. It is going to expand forever. The question is not whether the expansion will continue. The question is how fast it will accelerate, and what that acceleration will do to the structures we see around us. The most straightforward scenario, the one that fits the current data best, is the Big Freeze, also called heat death. The name comes from thermodynamics, the branch of physics that deals with energy and entropy. Entropy is a measure of disorder, or more precisely, a measure of how spread out energy is in a system. The second law of thermodynamics says that entropy always increases over time in a closed system. Energy flows from hot to cold, from concentrated to diffuse, from ordered to disordered. You cannot reverse that process without adding energy from outside the system. And the universe, as far as we know, is a closed system. There is no outside, there is no external source of energy. The total entropy of the universe has been increasing since the Big Bang, and it will keep increasing until it reaches a maximum, a state where all the energy is so spread out, so evenly distributed, that no work can be done. That is heat death. Not death in the sense of destruction, death in the sense of stillness. The universe will still exist. It will just be incapable of doing anything interesting. The timeline for heat death is long, absurdly long, longer than human brains are equipped to comprehend. Right now, stars are still forming, galaxies are still colliding, black holes are still feeding. The universe is active, dynamic, full of processes that generate light and heat and structure. That will continue for a long time, trillions of years at least. The smallest stars, the red dwarfs, burn hydrogen so slowly that they can last for tens of trillions of years before exhausting their fuel. But eventually the gas runs out. Star formation requires cold molecular gas to collapse under gravity, and that gas is a limited resource. Every time a star forms, it locks up some of that gas. Every time a massive star explodes as a supernova, it blows gas out of galaxies and into intergalactic space, where it is too hot and too diffuse to collapse again. Over time, the reservoir of star-forming gas gets depleted, galaxies run out of fuel, star formation slows, then stops. The last stars are born, the last red dwarfs ignite, and then nothing new. After that, it is just a matter of waiting for the existing stars to burn out. The biggest stars, the blue giants and supergiants, burn fast and die young. They are already gone, exploded or collapsed into black holes billions of years ago. The sun-like stars, the medium-sized ones, last about 10 billion years. The sun itself has about 5 billion years left before it swells into a red giant, sheds its outer layers, and leaves behind a white dwarf, a hot, dense core no bigger than Earth that will cool slowly over billions of years. The smallest stars, the red dwarfs, they are the last ones standing. They burn so slowly that the universe is not old enough yet for any of them to have died. The first red dwarfs will burn out in roughly 10 trillion years. The last ones will keep shining for 100 trillion years, maybe longer. But eventually, they all go dark. By the time 100 trillion years have passed, the universe is a very different place. Galaxies still exist, but they are dark. The stars are gone. The only light comes from fading white dwarfs, cooling brown dwarfs, and the occasional collision of dead stellar remnants that briefly reignites nuclear fusion before fading again. The cosmic microwave background, the faint glow of radiation left over from the Big Bang, has been redshifted by the expansion into microwaves, then radio waves, then wavelengths so long that calling them waves is almost meaningless. The universe is cold, the temperature is a tiny fraction of a degree above absolute zero, and it keeps dropping as space expands. The galaxies themselves are drifting apart. The ones that are not gravitationally bound to us, and that is most of them, are receding faster and faster as the expansion accelerates. The local group, the small cluster of galaxies that includes the Milky Way and Andromeda, will merge into a single giant elliptical galaxy over the next few billion years. That merged galaxy, sometimes called Milkomeda, will be gravitationally isolated. The other galaxies beyond the local group will have drifted so far away that they are no longer visible. The horizon, the boundary beyond which the expansion is carrying objects away faster than light can travel toward us, will have closed in. The night sky, if anyone is around to see it, will be empty except for the stars in the merged local group, and eventually even those stars will go dark. But the story does not end there. Stars are not the final stage. After the stars burn out, you're left with stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs cool over time, fading from white to red to black, eventually becoming black dwarfs, cold dense lumps of carbon and oxygen drifting through space. Neutron stars do the same, cooling into cold neutron spheres. Black holes, the collapsed cores of the most massive stars, do not cool in the traditional sense. They do not emit heat, but they do evaporate, slowly, very slowly, through a quantum process called Hawking radiation. Hawking radiation is a prediction of quantum mechanics applied to black holes. Stephen Hawking worked it out in the 1970s. The idea is that near the event horizon of a black hole, pairs of virtual particles are constantly popping into existence and annihilating each other. Normally, this process does not produce anything observable, but near a black hole, one particle in the pair can fall into the black hole while the other escapes. The escaping particle carries energy away from the black hole, and because energy is conserved, the black hole loses mass. Over time, this process causes the black hole to shrink and eventually evaporate completely. The smaller the black hole, the faster it evaporates. Stellar mass black holes, the ones formed from collapsing stars, take about 10 to the power of 67 years to evaporate. Supermassive black holes, the monsters sitting at the centers of galaxies, take about 10 to the power of 100 years. Those numbers are so large that they do not mean anything in human terms. A billion is 10 to the power of 9. A trillion is 10 to the power of 12. 10 to the power of 100 is one followed by 100 zeros. There is no analogy that makes that timescale comprehensible. It is just long, unimaginably long, but not infinite. Eventually, even the largest black holes evaporate, and when they do, the universe is left with nothing but photons, neutrinos, and a few stray particles drifting through an ever-expanding space that is approaching absolute zero in temperature. That is heat death. A universe that has reached maximum entropy. No stars, no black holes, no structure. Just a cold, diffuse sea of particles spreading out forever, unable to interact in any meaningful way because there is no energy left to drive interactions. Time, in a practical sense, stops. Not because time itself ends, but because nothing is happening. There are no clocks, no events, no changes. The universe exists, but it is static, frozen in a final equilibrium that lasts for eternity. That scenario, the Big Freeze, is the most plausible fate based on current observations. The expansion is accelerating. Dark energy shows no signs of weakening. The universe is headed toward a cold, empty, maximum entropy state, and nothing we see in the data suggests otherwise. But there is another possibility, a darker one. If dark energy is not constant, if it can change over time, if its strength can increase, then the universe could be headed towards something much more violent, the Big Rip. The Big Rip is what happens if dark energy gets stronger, not just stays the same, gets stronger, grows over time. If that happens, the repulsive force pushing space apart becomes so powerful that it eventually overcomes not just the gravity holding galaxies together, but the gravity holding solar systems together, the electromagnetic forces holding molecules together, even the nuclear forces holding atoms together. Everything gets ripped apart. First galaxies, then stars and planets, then molecules and atoms, then atomic nuclei. The universe does not just expand, it tears itself to pieces. The Big Rip is not favoured by the data. Current observations suggest that dark energy is constant or close to it, but the possibility is not ruled out. If dark energy is quintessence, a dynamic field that can evolve over time, then its strength could increase. And if it increases fast enough, the Big Rip becomes inevitable. The timeline for a Big Rip depends on how quickly dark energy strengthens. Some models put it tens of billions of years in the future, others put it trillions of years out. The uncertainty is large because we do not know how dark energy behaves over long timescales. We have only been measuring it for a few decades. Extrapolating forward billions of years based on that limited data is risky. But the mechanism is clear. If dark energy strengthens, the expansion accelerates faster and faster. Eventually, the acceleration becomes so strong that the distance between any 2 points in space is increasing faster than gravity or any other force can counteract. Galaxies lose their structure. Stars drift apart, planets are pulled away from their suns, eventually even atoms cannot hold themselves together. The electromagnetic force binding electrons to nuclei, the strong nuclear force binding protons and neutrons inside the nucleus, all of it gets overwhelmed by the expansion. Space rips matter apart at the most fundamental level, and then, presumably, the expansion stops or reverses, or the universe hits some kind of singularity where the laws of physics break down. Nobody knows what happens after that. The Big Rip is the endpoint where prediction breaks down and speculation takes over. The Big Rip is unsettling in a way the Big Freeze is not. Heat death is passive. The universe just runs down like a clock winding to a stop. The Big Rip is violent, active. It is the universe eating itself from the inside out. But again, the data do not favour it. Most cosmologists think dark energy is the cosmological constant, a fixed property of space that does not change. If that is correct, the Big Rip is not going to happen. The universe will freeze, not rip. But the possibility lingers because we do not fully understand what dark energy is. We know what it does. We do not know what it is made of, how it works, or why it exists. And until we do, we cannot rule out scenarios where it behaves differently than we expect. There are other exotic end scenarios that get proposed from time to time. Cyclical models where the universe undergoes repeated cycles of expansion and contraction, bouncing from Big Bang to Big Crunch to Big Bang again, over and over forever. Some versions of these models invoke quantum effects or higher dimensional physics to avoid the singularities that would otherwise end time and space. Other models propose that the universe could decay into a lower energy state, a process called vacuum decay, where a bubble of true vacuum nucleates somewhere in space and expands at the speed of light, rewriting the laws of physics as it goes. If that happened, the universe as we know it would end, not through a slow freeze or a violent rip, but through a sudden catastrophic phase transition that changes the fundamental constants of nature. Everything inside the bubble would be destroyed or transformed into something unrecognizable. That scenario is speculative. There is no evidence it is happening, but the fact that it is even possible that the vacuum we live in might not be stable is a reminder that the universe is not obligated to behave the way we expect. None of these exotic scenarios are supported by current data as strongly as the Big Freeze. The observations point to a universe that expands forever, accelerates steadily, and eventually runs out of usable energy. That is the consensus view. But the consensus could be wrong. Science does not deal in certainties. It deals in models that fit the data, and the models are only as good as the data we have. If new observations come in that do not fit, the models change. That has happened before. It will happen again. The expansion itself was a surprise when Hubble discovered it in the 1920s. The acceleration was a surprise when Perlmutter, Schmidt and Rees announced it in 1998. Who knows what surprises are waiting in the data we have not collected yet? What is not in doubt is that the universe will end. Not today, not tomorrow, not for trillions of years at minimum, but eventually. The stars will burn out, the black holes will evaporate, the galaxies will drift so far apart that they can no longer see each other. The cosmos will settle into a final state where nothing interesting can happen anymore. That is the future. And it raises a question that is harder to answer than any of the physics. What does it mean? What does it mean that the universe is finite in time, that everything we see around us is temporary, that the atoms making up your body and the stars lighting the sky and the galaxies stretching across billions of light years will all eventually dissolve into a cold, dark void? Does it matter that the universe is going to end if the ending is so far in the future that it is effectively unreachable? Some people find the idea depressing. If everything ends, if nothing lasts, then what is the point? Why build anything, create anything, care about anything, if it is all going to be erased eventually? That perspective misses something important. The fact that the universe ends trillions of years from now has no bearing on what happens tomorrow. The stars are still shining, galaxies are still forming, life is still evolving. The universe is not dead yet. It is not even close. And even when it does end, even when the last black hole evaporates and the last photon redshifts into nothingness, that does not retroactively erase everything that came before. The universe existed, galaxies formed, stars lit up the dark. Life appeared on at least one planet, maybe more. That happened. The fact that it does not last forever does not make it meaningless. If anything, it makes it more precious. The universe is not infinite. Time is not unlimited. What we do with the time we have, the structures we build, the knowledge we gather, the experiences we create, those things matter precisely because they are temporary. The endgame is written in the equations. The universe is expanding, accelerating, heading toward a cold, dark, maximum entropy state where nothing can change. That is the most likely outcome based on everything we know, but we do not know everything. The universe has surprised us before. It will surprise us again, and in the meantime, we are here, now. In a universe that is still full of stars and galaxies and motion and structure, a universe that is still interesting, still dynamic, still capable of producing moments of wonder and complexity and beauty. The end is coming, but it is not here yet, and that leaves room for something else, a future. Not the ultimate fate of the cosmos, but the immediate future. The next few billion years, the span of time that might be reachable, that might be survivable if we play our cards right. That is where the story goes next. Not to the heat death trillions of years out, but to the journey between now and then, to what happens to us, to life, to intelligence, as the universe continues its long, slow march toward the end. That is the final chapter, the one that asks not where the universe is going, but where we are going inside it. The universe is not going to wait for us to figure it out. That needs to be understood. We can debate the Hubble tension, argue about dark energy models, build bigger telescopes and design better experiments, and none of it changes the fact that space is stretching right now, carrying distant galaxies away from us at speeds we cannot match, pulling the future farther and farther out of reach with every passing second. We are not spectators in this. We are participants. Every atom in your body is moving through space at over 1 million kilometers per hour, caught up in flows and currents that span hundreds of millions of light years, headed toward destinations that shift and recede even as we approach them. And the strangest part, the part that keeps cosmologists awake at night, is that we are only just beginning to understand where we are going and why. Let's recap what we know. Start small. Earth is spinning at roughly 1,600 kilometers per hour at the equator, a rotation so smooth that you never feel it. The planet is orbiting the Sun at about 107,000 kilometers per hour, fast enough to circle the entire globe in less than 3 minutes if you could somehow peel that motion off and redirect it. The Sun, dragging its entire family of planets along with it, is orbiting the center of the Milky Way at roughly 800,000 kilometers per hour, tracing a path through space that takes 230 million years to complete one circuit. The Milky Way itself is falling toward Andromeda at about 400,000 kilometers per hour, a collision that will reshape both galaxies over the next 4 billion years. And the local group, the gravitational family that includes the Milky Way, Andromeda, and dozens of smaller galaxies, is being pulled toward the Virgo cluster and the Great Attractor beyond it, at speeds approaching 1,000 kilometers per second. Add it all up, account for all the layers of motion, and you get a total velocity of roughly 1,300,000 kilometers per hour. The speed at which you, personally, are travelling through the universe relative to the cosmic microwave background. That is your cosmic address in motion. That is the dance you are caught up in. The Great Attractor sits at the heart of that motion, at least locally. It is not a single object. It is a region of overdensity, a concentration of mass distributed across tens of millions of light years, pulling on everything within a few 100 million light years of it. The Milky Way is falling toward it. So is Andromeda, so are thousands of other galaxies scattered across Laniakea, the supercluster we live in. The pull is real, the motion is measurable. But here is the thing, the Great Attractor is not pulling the entire universe together. It is not strong enough for that. Its gravity dominates the local flow, the motions of galaxies within a few 100 million light years, but beyond that range the expansion of the universe takes over. Space itself is stretching, carrying distant galaxies away from us faster than gravity can reel them in. The Great Attractor is a local phenomenon embedded in a much larger process. It is a whirlpool in a river that is itself flowing toward a waterfall we cannot see. That duality, the tension between gravity pulling things together and expansion pulling them apart, defines the structure and evolution of the universe. On small scales, gravity wins, galaxies form, stars ignite, planets coalesce. Life appears, at least once, maybe more. On large scales, expansion wins. The space between galaxy clusters is growing. The voids are getting emptier. The filaments of the cosmic web are stretching thinner. And the balance between those two forces, the point where gravity can no longer hold structures together and expansion takes over, that line is moving. It used to be further out. As dark energy strengthens and the expansion accelerates, the boundary shifts inward. Structures that are not already gravitationally bound are being lost to the expansion. Galaxies that we can see now will eventually drift beyond the horizon, carried away by the stretching of space faster than light can travel back toward us. The observable universe is shrinking, not in distance, but in content. The number of galaxies we can ever hope to see is decreasing over time, and eventually, billions of years from now, only the galaxies in our local supercluster will remain visible. Everything else will have vanished beyond the cosmological horizon, lost to us forever. That is the future if dark energy stays constant. the Big Freeze. A slow, steady march toward maximum entropy, a universe that expands forever and cools forever until the last star burns out and the last black hole evaporates, and nothing is left but a cold, diffuse sea of particles drifting through space that is so empty and so cold that calling it a universe feels generous. That is the most likely outcome based on current observations. But we do not know for certain. We do not know what dark energy is. We know what it does. It pushes space apart. We know how much of it there is. Roughly 68% of the total energy content of the universe. But we do not know what it is made of, how it works, or whether its strength will stay constant over time. If dark energy is the cosmological constant, a fixed property of space itself, then its strength does not change. It was the same in the past, it is the same now, and it will be the same in the future. The expansion will keep accelerating at a steady rate forever. But if dark energy is something else, if it is a dynamic field that can evolve, then its strength could change. It could weaken, in which case gravity might reassert itself, and the expansion could slow down. Or it could strengthen, in which case the acceleration could increase, eventually becoming so powerful that it tears galaxies apart, then solar systems, then planets, then atoms. That scenario, the Big Rip, is not favoured by the data, but it is not ruled out. And then there is the Hubble tension, the mismatch between two independent measurements of the expansion rate that refuses to go away no matter how carefully scientists check their work. One method, using observations of the cosmic microwave background and running the equations forward to predict the current expansion rate, gives a value around 67 kilometers per second per megaparsec. The other method, using direct measurements of distances to nearby galaxies with Cepheid variables and Type Ia supernovae, gives a value around 73. That 6 km per second difference sounds small, but it is statistically significant, and it has persisted for years despite multiple independent checks. If the tension is real, if it is not the result of hidden systematic errors in one or both methods, then something in our model of the universe is wrong. Maybe dark energy is not constant. Maybe there is new physics we have not accounted for. Maybe the early universe was different in ways that affect how we interpret the cosmic microwave background. We do not know, but the fact that the tension is still there, still unresolved, is a reminder that our understanding of the universe is not complete. We have mapped the broad strokes. We know the universe is expanding, accelerating, dominated by dark matter and dark energy, headed toward a cold, empty future. But the details, the precision, the underlying physics, those are still being worked out. The philosophical implications of all this are hard to ignore. We live in a universe with a beginning and an ending. It started in a hot, dense state roughly 13.8 billion years ago. It will end trillions of years from now in a cold, dark, maximum entropy state where nothing interesting can happen anymore. Between those two endpoints, there is a window. A finite span of time when stars shine, galaxies collide, planets form, and life, at least in one corner of one galaxy, emerges and starts asking questions about where it came from and where it is going. That window is closing, not today, not tomorrow, not for billions of years, but it is closing. The stars will burn out, the galaxies will drift apart. The universe will settle into a final equilibrium that lasts forever. And when that happens, everything that ever existed, every star, every planet, every thought, every discovery, every moment of wonder or beauty or pain, all of it will be gone, erased by the relentless march of entropy. Some people find that depressing. If the universe is going to end, if nothing lasts, then what is the point? Why does any of it matter? That question misses something important. The fact that the universe ends does not make it meaningless. If anything, it makes it more meaningful. The stars are shining now, galaxies are forming now, life exists now. The fact that it does not last forever does not diminish the fact that it is happening. You do not need eternity to justify existence. You just need the time you have. And right now we have time. Not infinite time, not unlimited time, but enough time to explore, to learn, to build, to understand. Enough time to ask questions about the universe and sometimes, if we are lucky, find answers. The future of cosmology is being written right now. New telescopes are coming online. The James Webb Space Telescope is already delivering data that is challenging our models, finding galaxies in the early universe that are too massive, too bright, too structured to fit comfortably into the standard picture of how galaxies form. The Simons Observatory, a ground-based telescope being built in Chile, is designed to measure the cosmic microwave background with unprecedented precision, mapping the faint fluctuations in temperature and polarization that encode information about the early universe. The data from that telescope could help resolve the Hubble tension, or it could deepen it, forcing cosmologists to revise the models that have guided the field for decades. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will map the positions and redshifts of billions of galaxies, measuring the expansion rate at different points in cosmic history, with enough precision to detect changes in the strength of dark energy over time. If dark energy is evolving, if it is not constant, Romans should be able to see it. And then there are the experiments searching for dark matter, underground detectors buried miles beneath the surface, shielded from cosmic rays, waiting for a dark matter particle to collide with an atomic nucleus and produce a faint signal that can be distinguished from the background noise. Particle accelerators smashing protons together at near-light speed, trying to produce dark matter particles in the lab and measure their properties. Telescopes mapping the distribution of dark matter using gravitational lensing, watching how light from distant galaxies bends as it passes through the invisible halos that dominate the gravity of the universe. None of these experiments has found dark matter yet, not directly. But the search is ongoing, and every null result narrows the possibilities, ruling out models, constraining parameters, pushing the field closer to an answer. The discoveries waiting in the next few decades could be transformative. We could finally identify what dark matter is, what dark energy is, why the expansion rate measurements do not agree, whether the universe is headed for a freeze or a rip or something else entirely, or we could find nothing. The Hubble tension could turn out to be a systematic error that gets corrected once better data comes in. Dark matter could remain invisible, undetectable, its properties forever out of reach. Dark energy could turn out to be exactly what it looks like, the cosmological constant, a fixed property of space that does not change and cannot be explained. The universe could keep accelerating at a steady rate, expanding forever, cooling forever, with no surprises, no deviations, no new physics to discover. That outcome is possible, maybe even likely, but it is not guaranteed, and as long as there are questions we cannot answer, as long as there are tensions in the data, as long as there are mysteries waiting to be solved, the work continues. One of the hardest things to accept about modern cosmology is how much we do not know. We have mapped the large-scale structure of the universe. We have measured the expansion rate. We have traced the flows of galaxies across hundreds of millions of light years. We have catalogued the cosmic microwave background, the faint glow of radiation left over from the Big Bang, and used it to constrain the age, composition, and geometry of the universe with remarkable precision. And yet, we do not know what most of the universe is made of. Dark matter makes up 27% of the total energy content, and we do not know what it is. Dark energy makes up 68%, and we do not know what it is. Ordinary matter, the stuff made of protons and neutrons and electrons, the stuff that makes up stars and planets and people, accounts for less than 5%. We are trying to understand the universe using only 5% of the ingredients. That is not a small gap. That is a chasm, and it explains why the field is full of tensions, why different measurements give different answers, why the models work beautifully in some contexts and fail spectacularly in others. We are missing something. We just do not know what. The motion we are caught up in, the 670 million mile-per-hour journey through space that started long before we existed and will continue long after we're gone, is part of a story that is still being written. The local group is falling toward the Great Attractor. The Great Attractor is being pulled by the Shapley concentration. The Shapley concentration is embedded in a larger flow driven by structures we have not fully mapped. And all of it, every flow, every current, every gravitational tug, is happening inside a universe that is expanding and accelerating, carrying the largest structures apart faster than gravity can hold them together. The motions we observe today, the peculiar velocities of galaxies, the flows toward dense regions, the infall of matter into clusters, all of it is transient, temporary, a snapshot of a universe in transition, caught between the gravitational clustering that built the structures we see and the accelerated expansion that will eventually tear those structures apart. We are living in the middle of that transition, not at the beginning, not at the end, somewhere in between, in a universe that is still dynamic, still active, still full of processes that generate light and structure and complexity. But the clock is running, the expansion is accelerating, and the window is closing. The journey to the unknowable is not a journey in space. It is a journey in time. We cannot travel to the edge of the observable universe. The distances are too large, the speeds required are too high, and even if we could move at the speed of light, the expansion is carrying the edge away from us faster than we could ever reach it. The horizon is receding. The unknowable is not a place we can visit. It is a future we are being carried toward whether we like it or not. And the farther into that future we look, the less certain the picture becomes. We know the universe is expanding. We know it is accelerating. We know it is dominated by dark matter and dark energy. But we do not know what happens next. We do not know if the acceleration will continue forever or change course. We do not know if the universe will freeze or rip or settle into some equilibrium state we have not imagined yet. We do not know if there are other universes beyond ours, separated by barriers we cannot cross, evolving along different timelines with different laws of physics. We do not know if the Big Bang was the beginning or just one event in an infinite sequence of expansions and contractions. We do not know if time itself has a structure, a beginning and an end, or if it stretches backward and forward without limit. These are not small questions. These are the biggest questions anyone has ever asked, and the answers, if they exist, are waiting somewhere in the data we have not collected yet, the experiments we have not run yet, the observations we have not made yet. What we do know is that the universe does not care whether we understand it. It is expanding with or without our permission. It is accelerating whether we can explain it or not. The stars are burning, the galaxies are colliding. The cosmic web is stretching and evolving, carrying us along with it, toward a future we can measure but not control. And in the face of that, in the face of forces so vast and timescales so long that human intuition breaks down completely, we keep looking, we keep asking. We point telescopes at the sky and detectors at the ground and accelerators at each other, chasing answers to questions that might not have answers, building models that might be wrong, mapping a universe that might be unmappable, and we do it anyway. Because the alternative, giving up, accepting ignorance, stopping the search, is worse than failure. The universe is moving, and so are we, not just through space, but through time, through the brief window between the Big Bang and the heat death when stars shine and galaxies form, and intelligence, at least in one small corner, emerges and starts asking why. That window is all we get, and what we do with it, the knowledge we gather, the structures we build, the questions we answer and the new questions those answers generate, that is the only legacy that matters. Not because it will last forever, it will not, but because it is happening now, and now is all we have ever had. You're moving right now, through space at speeds that would vaporize anything not held together by gravity and inertia. You have been moving your entire life without feeling a thing, and the motion is not random. It is coordinated, layered, driven by structures so vast that we only discovered them by accident, while trying to answer smaller questions. The Earth spins, the Earth orbits, the Sun falls around the galactic center, the Milky Way plunges toward Andromeda, the local group drifts toward the Great Attractor, and all of it, every layer, every current is happening inside a universe that is not standing still. Space itself is stretching, accelerating, carrying distant galaxies away from us faster every year, pulling the future out of reach even as we try to map it. The question we started with was simple. Where is everything going? And the answer, it turns out, is complicated. We are falling toward the Great Attractor. We are being pulled by the Shapley concentration. We are riding flows that span 500 million light-years. But we are also being carried by the expansion, pushed apart by dark energy, moving toward a horizon that shrinks with every passing second. The destination is not fixed. It shifts, it recedes, and the farther we look, the less certain the picture becomes. We do not know what dark matter is. We do not know what dark energy is. We do not know if the expansion will continue forever or change course. We do not know if the universe will freeze or rip or settle into some state we have not imagined yet. What we do know is that the motion is real, the flows are real, the structures pulling us forward are real, and we are inside them, participants in a cosmic dance that started long before we existed and will continue long after we are gone. The universe is not waiting for us to understand it. It is moving, and so are we. For now, while ancient light still reaches us, every observation is a chance to read more of the universe's unfinished story.